Okay, and now the recording is started. As I said, welcome everybody. This workshop series has been organized by the World Climate Research Program, in particular in conjunction between the Lighthouse activity on climate intervention that I co-chair, and the Atmospheric Process and the Rolling Climate APARC. Our idea behind hosting this workshop was to have a platform that was available for researchers worldwide to share their research and to further discussion around the topic of assessing and understanding stratospheric aerosol intervention. As this discussion becomes more and more relevant societally, it is important for us and for the WCRP to make sure that what's being said about something like SAI is strongly backed by scientific understanding. And this is why we wanted to provide this platform altogether to make sure that researchers are able to give a glimpse to everybody else on what they were working on and potentially find new venues for collaboration and understanding. As a last thing, before leaving the floor to Mark, I wanted to thank in particular Indumathi and Liwa from the WCRP for helping organize this workshop, but we very, very specifically want to thank Mark Van Hobe, who's going to speak next, for having done a lot of the hard work of organizing and putting together this workshop, and being always on top of everything. And without him, it wouldn't have gone as smooth as it has up to now. And I hope this can continue. We really hope that this workshop can be of use to everybody. I also want to assure you that the recordings will be made available, the Q&A will be made available, and that there will be plenty of opportunities to somehow translate all that we learn throughout these 4 days into some kind of reporting out from our side that can be the beginning of a broader conversation about how to assess and think about SAI. So with that, I leave the floor to Mark that can give some more overview about the seminar.
Okay, yeah, thanks, Daniele, for these warm welcoming words. And yeah, I'm Mark, and I'm a co-lead of the Stratospheric Aerosol activity of APARC. And before we start, I want to point out a few things that hopefully help to run the sessions smoothly and not go into overtime. I already limits because the schedule is packed. And if you're a speaker, please take care to stay within the allocated presentation time of 3, 6, or 10 minutes, depending on what you selected in the registration form. Depending on that presentation time, you will receive a warning 1 or 2 minutes before your time's up. And if the time is up, we will tell you, and we may mute your mic if you don't come to an end yourself. Between the talks, there's 1 minute changeover time. And when you know that you are the next speaker, please get ready, unmute your mic, and then you can start right after the convener has introduced you. And there's 1 merged PDF per session. So there are 3 sessions today, 3 topical sessions. And if during your talk you want your slide to be changed, just please say next loud and clearly, and Liwa will move on to the next slide. And on each day, there are a couple of mini breaks in the schedule with 3 minutes each, and that will allow you hopefully to just have a little break to stretch, get a cup of coffee or tea, go to the bathroom, whatever, without missing anything of the talks. For the audience, please, if you have any questions to the talks, put it in the Q&A box rather than into the chat. However, we just noticed that it may be that the panelists and the speakers cannot put answers into the Q&A box. In that case, if you have an urgent question, please do put it in the chat, and we'll watch out for that as well. And you can, in the Q&A box, you can like popular questions, so they are moved up in the ranking, and we will select the most urgent and most interesting questions later for the discussions. In the session discussion, as well as the larger, longer block discussions we have on Wednesday and Thursday. And the organizers We'll also review all the questions and all the talks, and hopefully we can continue the discussions well after this workshop. First, to keep the momentum we gather here going, and also to give people a chance to take part in the discussions who are not able to attend all the sessions. And the WMO team, they will try to make these recordings. We're recording, as Daniele explained, the sessions available to all participants as quickly as possible after the session. You should have received the link in the email I sent earlier today. And with that, I hand over to Karen Rosenloff, who will share the first session, and look forward to an exciting meeting. Thank you.
Thank you, Mark. And so our first session is Strategies for SAI Detection, Monitoring, and Attribution. And our first speaker is Landon Rygar, who's going to talk about current and upcoming stratospheric aerosol measurements. So Landon, you can take it away.
Great. Thanks a lot, everyone, for letting me kick this off. So I'll just try to give a kind of a high-level overview of kind of the measurements that are currently being used to look at stratospheric aerosols and the future missions that are planned. Next slide. So I'll start with occultation. This has been a backbone of stratospheric monitoring from satellites since about the 80s. It's a really nice technique. It's got long path lengths, high sensitivity. It's basically direct attenuation from the sun. So it's very minimal assumptions that are required and very high quality extinction values that can be retrieved from these measurements. So next slide. This has kind of been the picture of what occultation missions have been up there. They started in the 80s with SAGE probably being the best well-known of the bunch. They had a gap between SAGE 3, but in 2017, SAGE 3 ISS was launched, and that's continuing to be operational, hopefully until the early 2030s, if and when ISS is deorbited. There's also, oh, sorry. Yeah, there we go. There's also a Canadian instruments on SciSat, Maestro and ACE-FTS that are currently up there. But following on these, for the future, there's not a lot of occultation planned. Unfortunately, the only one I really know about is Altius. This is a Belgian instrument, hopefully launched in 2027. It'll have a variety of measurement techniques, but one of them is occultation. So right now, kind of all of the occultation eggs are in the Altius basket, as far as I'm aware. But that said, there is still one planned, and hopefully this can continue this kind of long time series of high quality extinction baseline measurements. Next slide. Following on occultation, there's limb scatter. So this was kind of one of the next major techniques that was used. Similar geometry, long path lengths, lots of similar advantages that occultation has. However, because we're measuring scattered light, it means we don't have to wait for sunrise, sunset events, and we can get 10 or hundreds or even thousands of measurements per orbit. And very rapid global coverage over the sunlit portion of the globe this way. So you can really look at these events happening in much more real kind of time and in much finer spatial resolution. That said, you have to make assumptions about particle size and composition with these measurements. So they're not necessarily as high accuracy extinction if you get those assumptions wrong. So there's a trade-off there between coverage and extinction quality sometimes. Next slide. And for these, luckily, I think we're in a pretty good spot here. Right now, we've got OSIRIS still ticking along. It's probably on its last legs. But luckily, we have 2 OMPS measurements currently in orbit. These are limb profiler imagers in the kind of the visible near infrared range. There's 2 additional launches planned for OMPS in the future, 2027, 2032-ish. So hopefully those continue and with some good overlap, and we get good coverage from OMPS. There's some new techniques as well. Argos is a multi-dimension or multi-angle one with a test launch and then a further launch on the STRIVE mission, which will be an infrared imager. There's CART, which is another infrared imaging Fourier transform. I don't think this has been fully down selected, so it's maybe not confirmed yet or anything, but it's a potential candidate that could launch in the 2030s. There's also LE, which is a fully funded Canadian mission. It would launch as kind of a collaborative part of the Aerosol, or sorry, the Atmosphere Observing System, which is an American suite. But this is a Canadian instrument, and it would have some novel techniques in terms of looking at polarization from the limb. So I think in terms of limb scatter, there's lots of kind of exciting missions planned, lots of kind of like funded missions in terms of LE and OMPS. So I think limb scatter's in good condition. Next slide. Following this, we got LiDARs. So these are kind of the unrivaled in terms of horizontal and vertical resolution, very high resolutions there. Downside being because you're looking through the nadir, you have shorter path lengths and lower sensitivity to stratospheric aerosols, which can be pretty thin. But you also get polarization information, can measure day and night. And so there's lots of pros to a LiDAR as well. The kind of one of the downsides is they're expensive. So there's not a lot of them. So if we go to the next slide, this is kind of the state of LiDARs. So Calypso ended in, I think, 2024. And then there wasn't really anything to follow on immediately. But shortly thereafter, EarthCare launched, and that had the ATLID LiDAR on board that. And this has now started to bring stratospheric aerosol data down already. There's some early look stuff that looks really promising. The signal to noise is really good, and this looks like it'll be a great successor to the Calypso mission. And the launch for EarthCare went really well, so they have lots of fuel on board, and they're hoping to continue this mission into the 2030s now. So things are looking really good with ATLID. Following that, there's also with the aerosol, the atmosphere observing system is a LiDAR originally called Caligula. I think it's now been called Lucia. It's an Italian LiDAR. This would launch as part of that system, kind of in the early 2030s, and multi-wavelength polarization information. So hopefully with EarthCare mission being extended, and then Lucia as a follow-up, we'll have good LiDAR coverage as well for stratospheric aerosols. So not a lot of them, but hopefully there's enough there to keep continuous coverage. Next slide. In terms of nadir imagers, these aren't used as much for stratospheric aerosol directly. It can be difficult to disentangle the tropospheric signals, the typically pretty low vertical resolution, if any. So it's harder to measure stratospheric aerosol. But that said, after extreme events, people have come up with pretty novel techniques for looking at things like Hunga Tonga, some of the multi-angle polarimeters. You can pull altitude information out of that. And then, of course, they're also very important for the aerosol precursor gases. So looking at SO2 emissions and things like that. So I think it's also important to consider these nadir imagers when we're looking at the kind of the scope of stratospheric aerosol measurements. Next slide. And there's also a lot of these instruments coming online. So GEOS kind of Earth imaging ones, such as AVHRR, is currently operational, and there's follow-on missions planned to keep that going. There's hopefully multi-angle radiometer on the AOS mission, and then in addition to the OMSLIM profiler, it has imaging instruments on board as well. So there's VIIRS and OMS nadir mapper, and those will also be on the further iterations of the OMS satellites. So I think we have several more nadir imagers coming online, and things look hopeful, at least for the nadir pictures. Next slide. So then moving on to the ground-based stuff, I feel like I'm doing a disservice lumping this all into a single slide here, but these have really provided some of the longest running aerosol data sets we have. Because they're in situ, or they really have the ability to provide information not possible from remote sensing satellites. So they can get information on particle size and composition and things like that we can't get from space. So they're really critical in that regard. And typically, we often think of them with limited coverage, but recently more networks are coming online, and there's been some really interesting global campaigns to help mitigate this kind of lack of global coverage. Next slide. So this is kind of some of the longer term ground-based ones we have here. So we've got Garmisch, OHP, Mauna Loa, some of these big name LiDARs that have been around for decades and have provided really nice long-term time series. But in addition to that, there's been a few LiDAR networks that are continually being added to. So we've got MPLNet in North America, EarlyNet in Europe, Latin America has LaliNet now. And these are continually being built out with more LiDARs. Not necessarily all of them have the capability to reach into the stratosphere, but many do. And there's really interesting data sets here that help filling in the coverage gaps. So I think this is an interesting addition to the data set we can use. And then for balloons, there's the WOPC that were originally launched from Laramie, and then moved to Boulder, and these probably one of the best well-known data sets for balloons. But there's others as well. The B2 SAP has now been launching for several years. These have locations all over the globe, and it's a really nice data set to use, really high resolution particle size information. So I'd recommend checking all of these ground-based ones out as well if you're looking for stratospheric aerosol data. And next slide. So just to wrap things up here, on the left, you can kind of see all these things put together, and there's quite a bit kind of on this future, or the line between current and future. There's still a lot on the future, so I think things look relatively optimistic. You never know, missions can get canceled and things can happen, but at least there's lots of good plans. So that's nice. That said, we're still missing data. Aerosol is a very multi-dimensional problem. It's difficult to get particle size and composition and all the pieces of the puzzle we want from any individual mission. So really novel approaches and combining these instruments will probably be increasingly important, I think, in the future as we go forward. So there's been great work combining multi-angle spectrometers with LiDAR data, or looking at combining SAGE and ACE to get both visible and infrared data to get composition information, ways to combine ground-based and satellite networks. So all these kinds of integrated approaches where we're looking at data from multiple ways, I think will be important going forward and provide ways to help kind of fill in some of the gaps that we still continue to have. So with that, I'll wrap it up. Thanks a lot.
Thank you, Landon. We're going to take questions on all the talks at the very end, but if something comes up, please type it in the Q&A and Landon can even answer it in there. So our next talk is also on existing observations. It's Mahesh is going to talk about long-term stratospheric aerosol observations from GLOSAC and how they relate to SRM SAI. Go ahead, Mahesh.
Thank you. My name is Mahesh, and I work for SAGE Group at NASA Langley Research Center. In today's talk, actually, I'm going to talk about a long-term record of stratospheric aerosol observations from GLOSAC and their relevance to SAI assessments. Next slide, please. Yeah, so those who are not familiar with GLOSAC, I'll just start with what GLOSAC is all about. So GLOSAC stands for Global Space-Based Stratospheric Aerosol Climatology. And as Landon just gave a nice introduction about different types of instruments, and we are using some of the space-based instruments here to build this long-term record. It's a 45-year multi-sensor, multi-wavelength record, particularly 525 and 1020 nanometer of aerosol extinction coefficient. And the integral part of this long-term record is solar occultation measurements, SAGE, which is SAGE series of measurements. And at the same time, as you can see on the left side chart, there are limb scatter measurements and LiDAR measurements are also involved in it, which are very vital for this entire climatology record, particularly post-2005. So next slide, please. So so coming to the uses of GLOSAC, it's widely used data set now in climate modeling and observational studies. So and most recently, it is designated as the primary stratospheric aerosol data set for the upcoming couple model intercomparison project phase 7. And so that shows the scientific significance of the data product. And since 2018, we have published 3 papers on this, and we have over 300 citations combined. Next slide, please. So so the current status of GLOSAC, as I have just mentioned, for the post-2005, we have been relying on measurements from OSIRIS, which is a limb scatter measurement, and Calypso, which is a LiDAR measurement, and SAGE-3, it's a solar occultation measurement as well. But most recently, we have the Calypso is decommissioned about 2 years ago, and we have declining coverage of OSIRIS. So that being said, it's critical to continue and maintain CLOSAC product. So we are currently looking for the replacement of these two instruments, and then OMS is a potential candidate to replace OSIRIS and Calypso in the near future. So right now, with OMS, there are 3 different retrieval products available. Some of the recent studies have shown that there are differences between the product, and we are currently making efforts to reconcile the differences between the product. Next slide, please. So now coming to what is the relevance of this long-term record of GLOSAC to SAI assessments. So, well, on the right-hand side plot is the aerosol optical depth at 525 nanometer from GLOSAC. It's a time series of zonally averaged aerosol optical depth. And as you can see, it clearly, in the long-term record, we clearly have several volcanic eruptions and wildfires, and more particularly if you look at the Pinatubo eruptions around 1991, and you have El Chichon in 1982, and then more recently you have Hunga Tonga eruption in 2022 as well. So now what this gives is a long-term record, and then it's provides a baseline and put up states for in sort of SAI assessments. And as these are the natural analogs for any sort of SAI, stratospheric aerosol injection assessments. And this can also be used for constraining and calibrating the models. Next slide, please. So with this long-term record, what we have learned is that now we have seen several eruptions for the entire record, and more recently, from the SAGE-3 era, from 2017 till now, we have been having frequent volcanic eruptions and wildfires. What we have noticed is that each of these eruptions have been different in their behavior. So in particular, so if you look at the upper right plots, which is which provides 2 events actually. The first on the left-hand side, it is the Hunga Tonga eruption, and on the right-hand side, it's Ruang eruption in 2024. So for the Tonga eruption on the left, the blue line basically shows the aerosol extinction coefficient, and the red is the extinction ratio. So as you can see, the extinction actually peaks up following the eruption. That coincides with the dip in the extinction ratio. So extinction ratio is basically provides us information to infer aerosol size information. So the smaller the extinction ratio, the larger the particle size would be. So on the contrary, on the right-hand side, for Ruang eruption in 2024, it's totally the opposite. You see the increase in extinction, but at the same time, the extinction ratio is also going up. So that means that you have more number of smaller particles that creates the extinction higher. So what we learned from this is, it has different behaviors for this different events. And so it's very important in this case is to have multi-wavelength, reliable multi-wavelength measurements, particularly based on solar occultation measurements. And it can also provide us about transport, which is the bottom panel there. So that's from the zonally outraged extinction product following a Tonga eruption. So on the left-hand side, it is for March 2022, and on the right-hand side, it is for August 2022, basically showing the transport from the tropics towards the southern high latitudes. Next slide, please. Okay, so now having said this, we have challenges actually in the long-term climate record as well. So the main point here is that if you look at the data, the period between 2005 and 2017, so that's where we only had single wavelength measurements available, so no multi-wavelength measurements available during that time. So we had to rely on the single wavelength measurements to convert that. So basically, the figure here is the aerosol optical depth ratio plot, which is between the ratio between a 525 and 1020 nanometers. So this is exactly same as extinction ratio. So if you look at a larger extinction ratio, that means you have you're looking at smaller particles. So now in this particular time period,
So 1 minute left, Mahesh.
Okay, yeah. So we only had single wavelength measurements available. So it is particularly important to have multi-wavelength measurements available for the future measurements as well. And given the increasing frequency of fires and volcanic events, so this and future needs in assessing SAI, these measurements are really important, and a multi-wavelength instrument approach combining solar occultation and limb scatter measurement would be the ideal way to go about in the future to continue this record. And with that, next slide, please. Yeah, so that's the key takeaways. And with that, I'll conclude my presentation here. Thank you.
Thank you very much, Mahesh. And our next speaker is going to talk about the B2SAP effort that Landon briefly mentioned in his talk, and it's Alex Barone. Go ahead, Alex.
Yes, thank you, Landon, for introducing us, actually. So we're going to talk about in situ monitoring of the stratospheric aerosol layer, and we can go to the next slides, please. So we're talking about B2SAP, Balloon Baseline Stratospheric Aerosol Profiles. It's a NOAA Earth Reduction Budget Initiative project. You can scan the QR codes here to get to our website and get some more information. And next slide, you can click twice. So we are funded to characterize the background. Oh, go back a little bit. Yep. So it's about characterizing the background of the stratospheric aerosol, concentration and variability, and try to better understand what's going on after perturbation in terms of Earth's relative balance that this aerosol layer impact a lot. So we do that in the framework of that project with in situ observation from balloons, basically. We can go next. So as of today, and we started in 2019, the network we've been building up is looking like so. We try to have a latitudinally dispersed view of things of the stratosphere to map the best we can. And so the red stations are regular station where we try to have a good frequency of launches. The campaign sites are in green, and orange are future sites next to the equator where we have lack of data. You can click next to see our payload. Next, please. Yep. So the payload we are launching from these places is composed of POPS, portable optical particle spectrometer. It measures size distribution of particles between 140 and 2.5 microns, right? The accumulation mode of the stratospheric aerosol. We also have ozone and water vapor in general. So you can click next. The database right now, when you can scan it to scan the QR code to get to it, is composed of almost 200, I mean, a little more than 200 profiles, mostly from Boulder and all of these places. But please reach out to us when you have questions about the data. Next. Some of the questions we can address with that, starting with aerosol concentration above Boulder, for example, where we have the most statistics, is looking at the variability. So this is a profile of aerosol concentration in STP, and you can see that we have a really narrow variability above 20 kilometers, but we can still see individual plumes. Think of perturbation like eruptions. On the young layer down low, we have increased concentration and variability on this layer, and close to the tropopause, also high variability. Next, please. Another example is in the southern hemisphere above Florida, for example, where you have the average effective radius. Effective radius is a nice metric to compare to satellite retrievals, for example. So this is prior to Honga. You can click next and see how Honga impacted this effective radius. Basically, very large enhancement of particles. Click next twice now. And next again. And back to normal for the last 2 years, basically kind of relaxation of this stratospheric aerosol layer. You can click again, please. So just to conclude these 3 minutes, I think PeterSat tried to have this systematic and global aerosol in situ profiles from the stratosphere and try to address these critical needs, more fundamental understanding of this aerosol layer, assessing the variability and the background of this layer prior to anthropogenically modifying it. And this is building the capacity to monitor SAI or potential future SAI. And with that, you can put the last slide where I basically thank all our partners. Thank you.
Thank you very much, Alex. And now we will, and that was perfect timing. We will now move on to another talk about a balloon measurement network. And this is by Jean-Paul Vernier.
Thank you, Karen. And because we like balloon measurements here, I'm going to continue talking about that. I'm Jean-Paul Vernier from the National Institute of Aerospace. I'm based at NASA Langley Research Center in Virginia. And I'm going to speak about a new network for stratospheric aerosol observations that we call BALNEO. It's funded by the Upper Atmospheric Composition Observation Program at NASA. Next slide, please. First, I would like to remind everyone that stratospheric aerosol cycle is relatively well known, but still a complex ecosystem. Here is a modified sketch from Kremser et al. 2016. On this sketch, we see that medium volcanic eruptions, pyro-CB plumes, and also the transport of tropospheric sulfur, SO2, makes its way into the stratosphere. And those represent the largest sources of tropospheric aerosol, of stratospheric aerosol from the troposphere, with primary and secondary formation, especially for sulfur, but also with inorganic contribution, especially from pyro-CB. Next slide, please. As a result, satellite observations are really important and show us that the stratospheric aerosol layer is persistently variable. The stratospheric aerosol optical depth, shown here in this figure, was observed from the GLOSAC database, and it shows how small volcanic eruptions and pyro-CBs affected the stratosphere in the northern hemisphere, especially over the last few years. Next slide, please. This persistently variable stratospheric aerosol layer has been a motivation for us and for our team to deploy at multiple locations since 2014 to characterize the optical, microphysical, and chemical properties of volcanic and wildfire plumes, and also study the transport of Asian pollution into the UTLS region during the summer Asian monsoon. And all those balloon activities that led us to study the microphysical properties of those volcanic plumes or wildfire plumes led us later on to think about deploying and developing a network for balloon observation that we call BALNEO. Next slide, please. The aims of BALNEO is to assess the impacts of volcanic eruption, wildfires, and Asian pollution on stratospheric aerosol and climate, as well as validate satellite observations. So the first 2 flights of Balneo started in June 2024 last year from France and Brazil. The left figure shows the concentration profile of aerosols for different size bins. The flight took place from Brazil, Baru in Brazil, and provided measurements within the Ryong volcanic plume near 20 kilometers. The flight and the concentration profile on the right came from a flight from Reims, and near 10 kilometers, we see an increase in aerosol concentration, likely coming from North American pyrocybes. Next slide, please. So Balneo uses lightweight instrument to study stratospheric aerosol properties. One of them is used in the framework of Balneo is a commercially available optical particle counter tested and adapted for balloon flights with more than 30 channels between 0.3 and 10 micron diameter. We do also use the cobalt backscatter sound, a 2-wavelength sound to derive backscatter aerosol profile. And finally, we have used in the past an aerosol sampler for offline chemical analysis that we are planning in the future to use as a part of Balneo, as well as doing air sample for greenhouse gases measurements with aircore. Next slide, please. So over the past year, we have had 27 flights, including 10 in India within the framework of another campaign that we have over the past few years called the Betal campaign. So this is just the beginning of this network, and we are trying to expand with more sites. Next slide, please. Here is a series of measurements that was conducted from Reims in France between June and October 2024, showing the transport of the Ryong plume from the tropics to the northern hemisphere, as well as the impact of smoke from pyrocybin near the tropopause. So those flights here was the first 5 flights, and they helped us to look at the impact of the Ryong plume and smoke plume. The Ryong was seen near 16 kilometers between June and October, and the initial transport was from filaments, and then later on the transport became more important. The smoke layers that we observed over the 5 flights were very predominant, so we saw them four times out of the 5 flights. Next slide, please.
2 minutes, Jean-Paul.
Yes, this is also a motivation for us to have flights from France, especially looking at the effect of pyrocybes in the northern hemisphere. And so the flight from France included both aerosol and greenhouse gases measurements, especially CO, CO2, and methane. We used forward trajectory simulations from pyrocybes. Here is an example of pyrocybe in Canada from Manitoba. And we looked at those trajectories to try to plan those flights in France. In the case of the pyrocybe in Manitoba, Canada, it produced smoke layers that was transported across the Atlantic and which were detected in France on the profiles you see here. The 3 profiles show the aerosol concentration, and the middle one shows the CO and CO2, where CO and CO2 enhancement are located coincide with increase of aerosol concentration. Next slide, please. And finally, we believe that Balneo can be a tool for detecting artificial stratospheric aerosol injection once included into a more comprehensive detection system. Indeed, it is unlikely that random flights will detect any future SAI attempts, especially small. Rather, a framework that we can imagine where specific and targeted deployments would contribute to a detection system where further chemical analysis of stratospheric aerosol samples will likely play a major role too. Next slide, please. And I would like to stop here and let you read those conclusions and perspective. Thank you.
Thank you very much, Jean-Paul. We'll give people a minute or so to look at your slides. And our next speaker after Jean-Paul, and I apologize because I'm probably going to mispronounce your name, is Antonin Knizek, who's going to talk about stratospheric SO2 in the Earth Observation Data Group. So you can go ahead and bring up his slide. Thank you.
Yep. Hello. Thank you. So my name is Antonin, and I'm a member of the EODG Earth Observation Data Group at the University of Oxford in the UK. And in this short presentation, I wanted to give you a brief overview of the tools that we maintain and develop and use in the group. Next, please. So, the other way. Thank you. The group focuses mainly on satellite retrievals and on working with satellite data and their analysis. The main satellites that we currently use include the IRZ, the CRIS, or the TRPOMI, or the METOP satellites, which are nadir satellites. So as we heard in the first talk, these have very low vertical resolution, but can give quite a nice horizontal resolution. And we use the satellite data to retrieve the pressure profiles or temperature profiles or mixing ratios of species in the atmosphere. But crucially, we focus on volcanic eruptions and the retrieval of SO2, sulfuric acid, and ash particles. Next, please. So just quick examples of the 3 eruptions that we currently are looking at. It's the Raikoke eruption in 2019 and the Stratospheric eruption in 2021, both of which were rich in SO2 emissions, and also the Hangatonga-Hanga-Apa eruption in Tonga in the 2022, which, as you know, was very rich in water vapor emissions. Okay, next, please. So the first tool that we maintain is the scattering reference forward model. It's a general purpose line-by-line radiative transfer model, and it's designed to take properties of the atmosphere, such as the atmospheric profiles, scattering layers, and so on, and calculate the spectral response or the spectrum of radiation that the satellite would observe from the top of the atmosphere. It's designed for monitoring the effects of stratospheric SO2 on the chemistry and the physics of the atmosphere. So as you can see on the plot, these are the main species that we can fit in spectra from instruments such as IRZ. And these are the sulfuric acid, for instance, CO2, ash, SO2, ozone, water, and even N2O. Next, please. And then we use the forward model to develop satellite retrievals. We use the optimal estimation method to retrieve information about the atmosphere from the data. And some of the things that the model includes are precipitation, surface albedo, instrument response, etc. But one of the main points I want to make in this presentation is that it also includes cloud microphysics, which matters. Next, please. And it matters because, as we can see from this paper from 1992, the effective radius of aerosol really determines its response in the atmosphere. So we learned from this paper that if the effective radius of the aerosol population is greater than about 2 micrometers, and the extinction on the total greenhouse effect of the aerosol will exceed the albedo effect and cause surface heating rather than cooling. So this is something we have to bear in mind when we investigate stratospheric aerosol for climate intervention purposes. Next, please. And we also see from the model and the retrievals that scattering matters too. So just as an example, on this plot, there are 3 data lines which show the content of SO2, of sulfuric acid, and of ash in the eruption clouds from the Raikoke eruption in 2019. And so you can clearly see that all 3 components are present. And because we know that they overlap in the spectrum, we have to include all of them. Otherwise, we'll get the rest of them wrong if we omit one of them. Next, please. Okay. Another tool that we have is the Aerosol Refractive Index Archive, the ARIA database, which can be accessed from the group website. And it contains data on refractive indices for ash, acids, dust, water, ice, and other organic compounds. And it's open to everyone. So if ever you need data on refractive indices, please do not hesitate to use the database. Next, please. We also maintain a 50-year data set on SO2 emissions, It's maintained by Dr. Isabel Taylor, and again, it's archived on the Center for Environmental Data Analysis. And if ever you need data on SO2, please feel free to reach out. And these plots show just an example of the global multi-annual average for SO2 for 3 atmospheric layers from 0 to 5 kilometers, 5 to 10 kilometers, and then to 15 kilometers. So we can clearly see in this period where SO2 accumulates from various sources. Okay, next please. And we can also plot the data set to, see what volcanic eruptions which are attributed here do, but we can also use it to observe the effect of volcanic eruptions on the total budget. Okay, next please. And finally, we also dabble in climate models a little bit. So as you can see on the top left plot here, the total surface air temperature anomaly from the climate model in comparison project for the past 150 years or so is increasing in the recent decade. There's nothing new, everyone knows that. And equally, we can see on the plot that the red line increases much faster than the other two, and the red line represents the Arctic. So the Arctic warms faster, something again that is quite generally known. On the plot below, however, we can also separate only volcanic related anomalies and forcings in the model in comparison. And so we can see how the forcing changes after major eruptions, such as the Agung or El Chichon or Pinatubo eruptions, which are some of the major eruptions in the 20th century. And we can also see what the aerosol optical depth in the model the model ensemble is, and we can see that there's a correlation between the high aerosol optical depth after the eruptions, which may or may not be related to the eruptions. Okay, next please. And finally, we can take the same data and look at the latitudinal distribution of the total surface air temperature anomalies. And again, the plot on the top left shows that the Arctic is warming faster than the other latitudes, because the latitudes are on the vertical axis, whereas the time is on the horizontal axis. So again, there's nothing new there, but we can also clearly see on the top right plot that the volcanic surface atmospheric temperature, or the change in the surface air temperature after major eruptions, which are marked in the plot, decreases even in the Arctic. So that's especially true in the case of El Chichon and Pinatubo, which after which you can see clearly the blue color on the top of the plot. Okay, next please. Thank you. So just to summarize, the EODG, we have some tools and some expertise in stratospheric retrievals and in generally volcanic SO2 monitoring. And we have some tools that are available for the wider community, as for example, the ARIA database, which please feel free to use. And so since volcanoes are natural laboratories to study the SO2 behavior in the atmosphere, these tools are automatically also applicable to stratospheric aerosol and climate modification strategies. Okay, thank you.
Thank you very much. That was extremely efficient. Our next speaker is Anna Lang, who's going to talk about investigating the ability of satellite occultation instruments to monitor possible geoengineering. Go ahead, Anna.
Thank you. In the next few minutes, I give a quick overview of our results on the detectability of possible geoengineering experiments using satellite occultation instruments. Our results shown in the following are based on our paper published in ACP. Next. The aim of our study is to analyze using ECM-HAM simulations and transmission calculations and retrievals with the radiative transfer model SCIATAN, whether it is possible to detect the formed stratospheric aerosols from continuous emissions of 1 and 2 teragrams sulfur per year with currently active satellite occultation instruments, taking into account in error analysis and the natural variability. For more details on the methodology, I refer to our paper, but the basic idea is simply that the artificial aerosol enhancement is observable in a certain altitude range if the background profile is outside the error range of the retrieved aerosol extinction profiles of 1 and 2 teragrams sulfur per year. Shown below for the quasi-steady state phase with 1 and 2 teragrams sulfur per year, January and July, and illustrated here for 15 degrees north. And in all investigated cases, namely 1 and 2 teragrams sulfur per year in the quasi-steady state phase, the background profiles are outside the error range. Next. Also shown here for the SOID over latitude for 1 and 2 teragrams sulfur per year, January and July, and the quasi-steady state phase. And since in all cases the background profile is outside the error range, it can be concluded that the formed stratospheric aerosols from continuous emissions of 1 and 2 teragrams sulfur per year can be observed in the quasi-steady state phase for the latitudes and month considered here, which is not the case for the first month of the initial phase with 1 teragram sulfur per year, as shown below. But however, the natural variability has not been taken into account so far, and the geoengineering signal is considered detectable here if the corresponding SOED is outside the 2 sigma range of the natural variability, which is the case for the quasi-steady state phase and 1 and 2 teragrams sulfur per year, but not the case for the first month of the initial phase with 1 teragram sulfur per year. Next. And with that, some closing remarks. Thank you.
So I'll let you have a couple of a minute or so to actually read these concluding remarks. Thank you very much, Anna, for that very concise presentation. And we are now 3 minutes ahead. So our next speaker is going to talk about design of a CubeSat constellation, which sounds very interesting to me, and it's John Dykema.
Hi, so I wanted to start by thanking WCRP and the conveners for putting this together. It's great to see new and familiar faces here, and I've already learned quite a bit seeing what everyone else is up to these days. So I think this is a great opportunity. So today I wanted to present on behalf of myself and my colleagues at University of Chicago, Jim Franke and David Keith, the outline for a study that we're putting together, which would be to work with academic and industry partners to try to describe a constellation of small and inexpensive solar occultation satellites with where the metrics for evaluating the quality or the performance of this constellation would be the ability of the constellation to retrieve zonally averaged AOD and particle size distribution values, and particularly look at how efficient this constellation would be at monitoring a hypothetical deployment of SAI. So I think it's nice to have the background from Mahesh and Landon. The idea here of using solar occultation is certainly not that it's the definitive measurement, but it's perhaps the easiest to interpret. And also, I think there are available in the peer-reviewed literature some great designs for CubeSat compatible solar occultation measurement instruments for a space-based constellation like this. So we thought the existence of those instrument descriptions would kind of open up the space of potential players in this study and really allow us to partner maybe with some of the new space type commercial entities that may not have instrument design, but may have a lot of experience with instrument deployment and integration with CubeSat buses. So I think with that introduction, I just wanted to say we kind of envision that if this system were to be deployed, this could help complement and extend some of the existing stratospheric aerosol and particularly occultation records. Next slide, please. So this is should be somewhat familiar from what Landon and Mahesh said. This is from a paper by our colleagues talking about the impending data desert for satellite-based measurements of stratospheric gas phase composition. But I think this is a really nice cartoon that illustrates the real difference in sampling density between limb scatter measurements and solar occultation measurements. And some of this is obviously a repeat of what's been said before, but you have really favorable sampling, but more assumptions and more complex radiative transfer for the limb scatter in the top plots. And you have simpler radiative transfer and much sparser sampling for solar occultation. So that kind of is an illustration of why we wanted to start here with a solar occultation constellation. Next slide. And then finally, again, from the data desert paper, this is gas phase species, but I just wanted to highlight some motivation for the fact that there was a period where the stratosphere, people might have said, was quite quiescent or maybe even boring. And then in the past 5 years or so, there have been all kinds of anomalous events from enormous pyro-CPs, unusual dynamic anomalies, odd volcanic eruptions that produced a lot of water vapor and not so many particulates. And so I think the motivation is really strong to have a high sampling density with 3 wavelength retrieval available for particle size distribution for stratospheric aerosols to complement, as a capability to complement the other measurements that are going to be made or planned to be made, and to understand what seems to have become a much more interesting and complicated problem over the past few years. So I will stop there and let people think this over and see if they have any questions they want to ask, and turn it over to the next speaker.
Thank you very much, John. Very interesting. So our next speaker is Michael Hopfner, who's going to talk about observing stratospheric aerosol injection and its impacts using spaceborne infrared emission limb sounding. Go ahead, Michael.
Yeah, hi. Hi, good evening or morning. Next slide, please. We heard an introduction already about limb sounding instruments. So this, what I will talk about here, is an infrared emission limb sounding instrument, like MIPAS was, and you know, limb sounding has the high vertical resolution and the high sensitivity along the path lengths. About Fourier transforms, so we get a very broad spectral range of high spectral resolution. And infrared emission is that we don't measure the scattering of the solar radiation, but we measure the emission directly of the aerosol particles. So next, please. What we already I've mentioned, this was MIPAS, and with MIPAS, you know, from 2002 to 2012, we could measure vertically resolved H2SO4, so aerosol profiles, the total volume. So what we measure here is the total volume of the aerosol, the volume density, independent of the size. And the next is the other one was the SO2, which we have also measured with MIPAS. Next, please. What I will talk about here is a mission proposal we had for Earth Explorer 11. It's called CARE, the Charting the Middle Atmosphere in the Climate System. It was kind of a MIPAS mission, which we proposed to ESA in the last years. Next, please. And the CARE objectives, it's just the middle and upper, everything what is in the middle and upper atmosphere. So the changing of circulation, the wave driving, the coupling with the upper atmosphere, mainly also the impact of volcanic eruption and biomass burning, and the coupling between composition, circulation, and climate. Next, please. And that's the mainly observables here. So we get vertical profiles from the middle troposphere, upper troposphere into the lower thermosphere. And what is interesting here, what is of all these vertically resolved profiles all these things would be interesting to look at in case of geoengineering approaches. Next, please. So we, especially looked at also in one theme at these questions. So would CAD be able to detect an early small SO2 injection in case of SHG intervention? Then would CAD be able to follow SHG layer build up, and would it be able to observe the effect on stratospheric ozone? So as a baseline, we used from Simone here these WCRP CMIP6 runs, and this we put into in a CAD instrument simulator, which simulates the let's say profiles or the global distributions, and put on all the estimated errors which the instrument had, and looked at the result. So next, please. So on the left side here you can see this is 1 day of CAD observations, and the initial injection of SO2. For example, here at these 2 positions. On the right one, this is at 1 altitude, and in the right side you can see just a cross section through one of these orbits in case of SO2, and the model true. So that's the real model, and then simulated observation. So that's the CAD measurements. We've added all the errors, and we got the result that CAD can detect even half a ton to 1 ton of SO2 dispersed over a region of 100 times 100 times 1 kilometer in the lower stratosphere with this altitude resolution. So it would be suitable to look at the initial onset of SO2 injections here. Next, please. Then in the spectra there is also this SO2 this H2SO4 aerosol signal, where we simulated here the volume densities or the mass of H2SO4 aerosols as it evolved after the initial initial setup of the intervention. And you can see here on the top is the model, and the lower part is just some days of aerosol measurements, which would be possible with CAD. Next, please. What we also looked is at the ozone total columns here. So from the vertical profiles, we can of course then also look at the total columns. So and here we can see that ozone, of course, is a major gas which would be affected by geoengineering, and we could measure this with CAD very well. Next, please. So this just tells you that we can also resolve vertically the profiles and the distribution changes in case of geoengineering. Next, please. So that's the last few graphs showing what we would, so that the CAD observable, what would be possible. So SO2, H2SO4, stratospheric warming, the temperature would be measured very accurately, water vapor, then change in circulation due to age of air, SF6, CH4, and so on. Stratospheric chemistry, we have would have all these gases like MIPAs would have, so the effect on the stratospheric chemistry could be observed, and of course the changes in ozone due to the change in stratospheric chemistry. Unfortunately, we had the last round. We reached the final after 5 years in this ESA selection round of EE11, and unfortunately CAD has not been selected this time. But as you can see here, and you can read here, it seems to have been a very hard competition with the other instrument, and we had a good support of all middle atmosphere people and so on, but it didn't help this time. So but of course we will try on to have these measurements, to make these measurements possible at one time. Thanks a lot.
Thank you. And I'm sorry to hear that Carrot wasn't selected, but we can keep our fingers crossed that maybe you get another opportunity. So our final talk in this session is on observational requirements that you would need to quantify stratospheric aerosol injection. And our speaker is Frank Koich. Go ahead, Frank.
Hi, thank you very much. I want to thank the speakers for letting me present, and I have some of my co-conspirators on this talk listed here, David Keith, Rick Smith, and Doug McMartin, although thoughts from a large number of people comes in. And I think what I will be focusing on is sort of a nice build-up of the session, which is sort of really thinking about for deployment specifically, what are the what observations would be needed. And a lot of the previous measurements set the context for that, and in fact mean I can skip some of the context I have. Often, I think when you talk to a stratospheric aerosol injection scientist, they say, you know, what are the measurements we need when we do deployment? But I think it's really important that to realize that really this baselining of the stratosphere, which is beginning, but I would say currently insufficient, is actually required at least a decade before you would start any geoengineering to make sure you understand the actual system you're perturbing well enough. And so I'm going to split it up into sort of three parts. First is sort of baselining and why before deployment, then research specific to deployment, that where I'll talk about existing analogs and perturbative experiments. And lastly, I'll talk what maybe perhaps need to be taken into account for deployment in addition, and that will actually go beyond the stratosphere. If you could go to the next slide. So first for baselining, a lot of people when they talk about stratospheric aerosol worry about stratospheric ozone. That is well deserved, but I actually think the impact from sulfuric acid on dynamics is a much larger, a less well constrained question. What I'm showing you on the left-hand side are stratospheric temperature anomalies resulting, you can see the trend in decreasing temperatures from greenhouse gases, and then you see these perturbations from El Chichon and Pinatubo that increase the temperatures of the stratosphere. Why should we care about this? On the right-hand side, I show a figure from the recent previous WMO ozone report. And what that shows is the change in age of air, so the dynamic response of the system to the greenhouse gas and perturbations. And what you can see is that the models agree fairly consistently that there should be a speeding up of stratospheric circulation of about, let's say, 0.1, 0.2 degrees years per decade, and that the only observations we have, if we try to get the age of air from that, we see that that actually indicates a slowing down of the overturning circulation. And I'm not saying that this is right, but I think it means that this is something we need to pursue more. And what I would actually argue is that one of the things we've seen in the previous slides is a really strong focus on stratospheric aerosols and the quantities and all of that, and that's great. And in CARET right now, we saw a little bit, there was a focus on tracers, and I actually think observations of tracers that give us a better understanding of trace gases that give us a better understanding of stratospheric circulation is actually a prerequisite to understand whether you might be messing with stratospheric circulation if you do stratospheric aerosol injection. Next slide, please. The other part that we also, especially for stratospheric, for SAI injection, which likely would occur from airplanes, from point sources, is the question of how well we understand small-scale stratospheric turbulence. And what this slide is supposed to show, what it shows on the right-hand side really is that if you look at the conditions under which you would expect turbulence based on measurements we have, where you can look at the Richardson number, and you look at where you actually see stratospheric turbulence in these vertical profiles, those two, you should see stratospheric turbulence at very low Richardson numbers is when you would expect that. And sometimes you see that, sometimes you don't. And so I think a better understanding of small-scale stratospheric turbulence, because of that, could impact how quickly a plume disperses and mixes into the background stratosphere, especially close to injection, is something else that could be useful to have better observations of and model studies. Next slide. Then the other part, we've heard about this. I will essentially not say much. This refers to a previous talk where we saw that when you have injection of sulfuric SO2 in the stratosphere, depending on the details of the volcanic eruption, what happens to the aerosol size distribution can vary. And I'm showing here a study from Felix Rana, and also a study that we did that showed that after the Soufriere eruption, which was a fairly small eruption, the models predicted a larger particle size for quite a while, whereas actually the observations showed a fairly persistent smaller particle size, at least for this system. And we saw some previous very nice talk that sort of showed how complicated and individualistic these eruptions are. And so more observations for better understanding of aerosol microphysics are valuable. And we've seen B2 sub and many other presentations today that really can aid in this, as long as we get the continue getting the nice spread of volcanic eruptions that would help with the science. Next slide, please. Now I want to say, why for SAI, where in the aerosol microphysics, this is partly aerosol microphysics, when you look at SAI model predictions, where there's still uncertainty, and it's important to see what observations can help with that, is what you're seeing in these two figures is you see a comparison of 5 different models. And you see this is from the WM ozone report again, for the 2022 one on ozone. You can see how the forcing you get and the temperature change you need for 1 Kelvin. You can see that in different models, quite different injection amounts are needed to get to sort of the same forcing and or temperature change. Now, a caveat for that is that in these 5 models, they weren't all done under exactly the same conditions. So the scenario development is something to be careful about, but it shows that there could be something in the aerosol microphysics or the dynamics of how it's represented in the models that we also need to work on if we think about SAI deployment and what impacts it could have. And so if you think about a factor of 2 difference in cooling from the same, or you have to double the amount of SO2 you inject depending to get 1 degree Kelvin. Now, one could argue that's a significant uncertainty. So we need improvements on that, and observations and models working together could help with that. Next slide, please. I want to briefly talk about analogs and the question of whether we've really used all the different analogs we have in the right way if we're really trying to understand SAI scenarios. There's a lot of volcanoes, and you can see that I'm trying to map out here different scales of perturbations that happen that go sort of from volcanoes to pyro-CB events and convection. There's a sliding scale towards convection there, overshooting convection, and that can go up to 19, 20 kilometers and injects much smaller amounts of mass than you get from volcanoes. There are rocket plumes, there's aircraft plumes. And then the question is whether you could actually inject particles that not act for cooling, but actually act as tracers of an evolving plume, for example, that you could look at this. And if you go to the next slide. So one of the examples I want to focus on, there are pyro-CB events, but on the right-hand side, what you're seeing is a supercell over Kansas that we used the campaign I was part of, DCOT's campaign, where there was a small overshooting event. And what you see in the bottom part is what we did in that campaign is that the initial, perhaps say 1 kilometer size or a little less amount of ice that was injected to 19 kilometers in the stratosphere, we used 4 forecasting models to tell us where it would end up in about 3 days after the event. And we sent the ER2 there, and we were able to find this plume of water. As you can see, the plane ascends, and then from these points P1 to PA, it actually goes through this plume, and we were able to find this plume remarkably well. So what this shows is, for example, this question of how does a plume evolve in the stratosphere that's smaller than a volcanic plume. I think, for example, these overshooting events could give us some test beds for how quickly does an air mass actually spread out. We sent the plane and really got cross sections of the plume a few days later and how the water had spread in this. If you go to the next slide. Of course, there are rocket plumes one can study to look at smaller scale perturbations even in that. And this has been done before, but in a very, very limited amount. And if you go to the next slide, there's another rocket plume study. I just want to show these and say that this has been done, but what I'm showing you here is a significant fraction of the rocket plume studies that have been done. And they have been useful for modeling how the rocket plume evolves and how the chemistry in it evolves. If you go to the next slide, here is an example of a few studies that were done when you had the ER2 sampling its own plume in the stratosphere. And that really provided some very interesting insight together with a modeling study about how the vortices of the plane dissipate in the stratosphere over time by looking at the chemicals as a tracer of that dissipation. So there are a few studies of that. One of the things I want to point out with these analogs, when you're trying to study a rocket plume or a plane finding its own plume, these are very hard studies. These are very limited number, and actually doing this successfully in the right way is very difficult. And the question whether they give you all the information you would actually want for understanding what would happen to the stratospheric aerosol injection of SO2 is an open question. So you can definitely learn a lot, and we probably haven't done enough to learn about that, but there are limitations to what you can learn from analogs. If you go to the next slide. So that brings us to perturbative experiments, and that is that for some aspects, for example, the question of how quickly does SO2 actually get oxidized and turn into sulfuric acid if it was injected from an aircraft in a plume. That is something where all the previous studies can give you some information, but in the end, I think you actually would need an actual experiment to tell you about this. The things you would want to know is there's been some work on sort of including things like the slow plume dispersion, vortex dissipation, the question of how important ion-induced nucleation is in the outlet of the engines, if that were to happen. And this question of how quickly does it actually mix in of this plume with a complex background, depending on conditions, is something I don't think we have a good enough answer for. And one of the points I will make is that I think if you did these studies, you actually would not just want to inject SO2 and follow the SO2 injection. And it was really interesting to see that in what the previous talk, that you could see there's 1 ton of SO2 being injected. That's actually quite interesting in this context. But you would probably also want to add a passive tracer that tells you the actual dilution of the plume, and you would want to sample through that plume multiple times. And so thinking about what kind of sampling measurements platforms actually are needed for this is something that hasn't been done to the degree I think would be needed. If you go to the next slide, and that actually is my final slide for this. And when you think then about actual deployment, of course, what we're talking about here, there's a big focus on the actual stratosphere. And I think, of course, you need a whole array of measured quantities in the stratosphere from all the platforms that we have seen in the previous talks, balloons, aircraft, ground-based, and obviously satellites, and they have to be combined with modeling. To me, some of the key metrics are top of atmosphere spectrally resolved radiation to actually see what's happening there, temperature profiles throughout in the atmosphere. We need to get good quantification of the dynamics. Again, I think the measurement of tracers in the stratosphere that allow you to really understand how dynamics are evolving is one of the biggest gaps we have in current observation in the stratosphere. And I think so I really want to emphasize that I think that's a key quantity that we can actually find out what is happening to stratospheric dynamics. Aerosol distribution, as you descend through the atmosphere, cirrus cloud properties, the amount of cirrus cloud as particles may come down, what is really happening to clouds, and obviously many more important. It is important in the discussion about observations that would be needed for stratospheric aerosol injection and deployment is that you would also need a whole array of measurements on the ground. And that baselining of those would also, I think, have to happen a decade or so. I'm making the decade up. I haven't quantified this before you actually do any deployment. Temperatures, diffuse versus direct light, very important quantity. Surface air composition chemistry, aerosol size distribution. I think also you want surface spectrally resolved radiation, meteorology, hydrological cycle. So I think the summary of my talk overall is that the baselining of all these parameters, both for the stratosphere and for the ground, really has to be in place well before any deployment could occur. And I think there's some significant gaps we have in those for what is really needed to answer of things that are not only specific to SAI, like the tracers, but are also specific to SAI. Thank you. And I want to thank the organizers for letting me present about this topic.
Thank you, Frank. That was a great summary of a lot of things that I definitely agree with. So this concludes the talks for this particular session today. We have a few minutes for additional questions. If you take a look at the questions and answers, a few of them, or all the ones that have been entered pretty much have been answered, but I will read, and it looks like Frank is. Go ahead, Frank, and just answer Gregory Slater's question orally.
I am really sorry if it came across that way. What it emphasized is a need for baselining measurements well before there's any consensus. And largely, I think the baselining measurements, like the traces, for example, I think are useful broadly. The idea of small-scale deployments is something that I did not say that one should do these right now. These clearly would have to come before deployment, but my emphasis on what has to happen right now with baselining did not include small-scale deployments as deployments. For me, small-scale deployments are not baselining. Those are specific SAI-specific research questions what would want to follow, but they are not baselining. I'm apologize if I misrepresented that. And if that's not clear, please follow up.
Thank you very much, Frank. If you take a look at some of the other questions that were asked during the session, there were some specifically about details on the instrumentation. And then there was one I wanted to highlight that was asked to Mahesh from Anna about why was the EarthCare not a candidate to replace Calypso. And Mahesh, if you want to go ahead and just address that to everybody, I think that would be useful. If Mahesh is still there.
Yeah, I'm here. Yeah, so we'll definitely look into Adelaide. So I responded that in the chat as well. So if I understand it, the wavelength is at 355 nanometer, and GLOSAC wavelength is at 525 and 1020. So again, we'll have to do the conversion again there. But given that, I think, I know that it is HSRL. So I was expecting actually to get an extinction product from there, but I recently came across a paper that basically use a fixed LiDAR ratio of 50 to convert that to the backscatter extinction to backscatter to extinction coefficient. So that's what I was wondering. So I don't know why. I was expecting an extinction product since it is HSRL. So I don't really know. I've been looking actually at the data, but I didn't get the data product yet. So I'll in future definitely look into that for sure. Yeah.
This sounds like a great way for you guys to interact with the Europeans and get some of the information that you actually need. If anyone else has any specific questions, let's see, I have two more open ones. Well, that's not really a question. I had one question, and this was involving the carrot that Michael Hoffner talked about. Michael, is there any chance that you will be submitting this instrument to another potential call or looking into other ways to get it deployed? Because I think, Frank mentioned the need for gas phase measurements too. Carrot is the kind of instrument that would be ideal for a lot of things that we need.
Yeah, sure, we will try it, every street which is open, but at the moment now, it's not really clear how to go forward. Okay, make a smaller instrument, to try to make smaller instruments to get on a road, which is possible for smaller instruments. We are trying this, but at the moment, that's the ESA selection rule. It's if there is a final decision, you are out, and then we will see.
Well, thanks. So we do hope it comes to fruition at some point. I know you all have been working on this for actually a very long time, longer than just 5 years. And then the other hope is there's another instrument that may give some of this information that's under consideration right now, which is called STRIVE. Whether the US will fund any earth science, I have no idea, but there is hope that will actually happen.
Yeah, it would be good.
Yeah,
Of course.
and not seeing anything else in the Q&A. Do any of our speakers or other panelists, organizers have any questions that they want to ask at this time? And not seeing anything immediately.
Yeah, Carol, I have one for Frank.
Sure, go ahead.
Frank, I mean, you have been involved in trying to do some small scale deployment. And so I would like to have your thoughts about why do you think we need small scale deployments and why natural analogs, we have plenty of volcanic eruptions, we have a lot of pyroCBs, are not sufficient to learn what we need to learn.
Right, and I actually don't quite know. A small scale deployment is an interesting term. So I think there are processes that would occur if you inject from a plane that could be at that involve a scale that is smaller than the scale that you get from a volcanic eruption, because you have the scale from, in essence, the nozzle on a plane to a few kilometers, right? Whereas volcanic eruptions are much larger size. So it is, I would fundamentally, one of the questions in that is that if you think about the representation of how SO2 shows up in a climate model, right? It's in a grid box that's very large. One of the questions is, does that initial plume evolution and the perhaps nonlinear chemistry you may get in that plume end up with the same aerosol size distribution as if it showed up in the model at the scale that you would have in that grid box? And I'm not a modeler, and I see Simona is moving around, and I'm probably making her uncomfortable. But I think they are fundamentally processes that are sub-grid scale that a volcanic eruption probably can't tell you all about. I'm not saying those are the most important aspects, but they are certainly there. And there's some initial studies using, trajectory models. You can use LES models perhaps to try and understand that better. But if you really want to know what you have that right in the end, probably one could imagine that there are some subgrid scale, and I see their hands going up. I think some small scale experiments could be useful. I wouldn't call those deployment because they're actually not trying to perturb anything, right? They're not trying to have any effect on the surface. But they are fundamentally, I would say, these are experiments to understand the dispersion of a plume in the stratosphere and how well we understand that.
Thanks,
Thank
Frank.
you.
And Anna, did you want to say something?
Wasn't
Because I saw your hand up.
it out, but really just saying that if you have small injections, it will be hard to detect and to find the plumes. And that's, of course, something you have thought about, but that's something we need to discuss and think about. What is small scale? How small is it? What can you do? And one thing from Michael Höpfner, of course, interestingly, what can you detect even when you do an initial, injection of smaller particles? Just my comment.
Thank you, Simona. And then we'll give the last word to Ron Byman. I apologize if I said your name wrong, because it sounds like looks like you have your hand up and a comment you want to make.
Yes, please. Thank you. Thank you very much for all these excellent presentations. I had a question from the kind of social science perspective. It seems we're about to cross 2.0 Celsius in the late 2030s or early 2040s if the current rate of warming continues. Isn't it time to, I mean, more data is excellent. I fully support all experiments and efforts to gather more data and understanding, but at some point we have to evaluate the risk versus risks, of delaying deployment until the human and species consequences become really calamitous, or potentially calamitous, versus collecting more data. So I would suggest, I mean, I'll get into this in my talk, but perhaps, it might be useful to consider the situation now of more of a engineering optimization situation rather than let's not dare talk about deployment for fear of calamitous risk situation.
If we got anyone who wants to.
It's a general question, I know.
Yeah. And that may be something to think about. We do have a lot more time to do a discussion on Wednesday and Thursday and after your presentation as well. So does anyone want to say anything specifically? And if not, I think why don't we remember that point, which I think is an interesting one to address, and that gets into the whole geopolitical sphere too. And then it looks like what we have is a mini break scheduled. So you have 5 minutes to go get your cup of coffee. And then we will come back in with global and regional climate impacts of SAI. And I forget who is chairing that session, but we'll see you all in 5 minutes. Thank you. And thank you everybody for keeping to time, that this was an easy session to monitor.
Okay, hey Mark. While people slowly getting back, I just wonder if we should start sharing already the next talk. It is 35 minutes after the hour, and all people coming back. Welcome everybody. This is our second session. Today, this one is about global and regional climate impacts of SAI. I have a nice set of speakers as previously. please put your questions in the Q&A. And if you can't reach it, you can also put it in the chat. Also, if you're a speaker, you can answer the Q&A during the session, and we'll have a discussion at the end. So what we will start with is a recorded talk by Andrin Juriman on the effects of SAI in the middle atmosphere across models. Okay, I think we can go ahead and start.
Hello everyone, I'm Andrin Juriman, and I will quickly talk about the multi-model perspective of the effects of a stratospheric aerosol injection. This is based on the CCMI 2022 experiment, and essentially there are two runs. There's SENDI2 SAI, which simulates a relatively strong stratospheric aerosol injection, which can be seen in this layer above the tropopause in the surface area density. And this layer offsets the surface warming of a moderate climate change scenario. And then there's SENDI2 fix, which does not have the enhanced stratospheric aerosol and acts as a reference to compare against. So by taking SAI minus fix anomalies, we get the signal of the aerosol injection. And there are 5 models that contributed data here. So looking at the ozone anomalies, we can see that, so this is a multi-model mean, and everything that's hatched here means that the models do not agree on the sign of the change. But let's first look at what they do agree on, and it needs to be mentioned that these aerosol particles cause strong heating in where they reside, and this comes with an intensification of the circulation, the deep branch of the Brewer-Dobson circulation, and so and also a strengthening of the polar vortices in general. And in region 1, shown here, air with less ozone is sucked up into this region, so there's a negative anomaly. Higher up, the more intense circulation provides more water vapor, which hydrolyzes reactive nitrogen compounds, which usually destroy ozone. So there's a positive ozone anomaly from this hampering of this mechanism. But even higher up, the opposite is the case, and basically more reactive nitrogen and hydrogen oxides can react with ozone, destroying it catalytically. Just above the Antarctic tropopause in region 4, the abundance of the aerosol particles is responsible for the activation of chlorine through heterogeneous chemistry, which causes ozone loss as well. So now let's look at the lowermost tropic stratosphere. And here, if we look at one of the reservoir gases of chlorine, we can see that in this time series, the 5 models, the anomalies of hydrochloric acid in 5 models is shown, and some are negative and some are positive. So essentially, the models disagree on the chlorine partitioning between reservoir and active gases, which controls ozone. And finally, above the Arctic, what we find when we look at the active chlorine here is that there's a very large spread between the models. And for one, there's heterogeneous chemistry that may be treated differently in the models, but also this polar vortex strength correlates with the temperature at the pole. And we find that the temperature trends are quite different between the models. And this then has a control on the chlorine activation, which is where part of this difference in ozone comes from, hence the models don't agree there. So that has been the quick overview, and I wish you a nice conference or workshop. Thank you very much.
Yeah, thank you, Andrin. And the next speaker now will be, I think, Evie Glade. I hope I say your first name right. Comparing future projections of warm spells and their characteristics under climate change and stratospheric aerosol injection in CSM2 and UK ESM. Thank you. Please unmute yourself and go ahead when the slides are up. Thank you.
Okay, awesome. Yeah, so just waiting for the slide to load here. Okay, well, hi everyone. I'm happy to be giving a talk today in this virtual workshop. But today I'm going to be talking about some of my dissertation work, which compares future projections of warm spells under climate change and stratospheric aerosol injection in CESM2 and UK ESM1 next. Okay, so extreme heat events are projected to increase in frequency, intensity, and duration as global temperatures rise. And this is shown here in the figure on the left, which shows the number of days where daily maximum temperature is projected to exceed 35 degrees Celsius when global warming reaches 1.5 degrees and 3 degrees Celsius of warming. And so the work I'm going to be presenting on today focuses on a particular type of hot extreme called a warm spell, which is defined as a period of anomalously high temperature that can occur at any time of the year. And compared to warm season hot extremes, less work has examined future changes in warm spells, which impact human and natural systems in and outside of the warm season, including human mortality and morbidity, crop and livestock yields, energy demand, ecosystem vulnerability, and snowpack mass loss. Next. And so the questions I'll be addressing in my talk are, one, how might warm spells be impacted by climate change and SAI? And two, are future projections of warm spells model dependent? Next. So I compared future projections of warm spells in CESM2 and UKESM1. In both models, I considered a climate change simulation that was run under SSP 245 from 2015 to 2069. I considered simulations of SAI deployment from the ARISE SAI 1.5 simulations, which run from 2035 to 2069. And the principal goals of SAI deployment in these simulations is to maintain global mean temperature at 1.5 degrees Celsius above pre-industrial. And so in each of these simulations, I defined warm spells throughout the simulation period as any period throughout the year where the 90% threshold of daily maximum 2-meter temperature was exceeded for at least 6 consecutive days. The 90% threshold of daily maximum temperature was calculated relative to the period in each model where global mean temperature reached 1.5 degrees Celsius above pre-industrial. Next. Okay, so these figures show how show annual mean warm spell event frequency when global mean temperature reaches 1.5 degrees Celsius above pre-industrial. In CESM2, which is shown on the top, and UKESM1 shown on the bottom, we can see that the spatial pattern of annual mean warm spell occurrence is relatively heterogeneous, and that warm spells are rare events occurring only up to 3 times per year. Next. And so under SSP 245, shown here in the center column, warm spells are projected to increase in frequency in both models, with increases being as high as 5 times the reference average. Next. Finally, shown here in the right column, when SAI is deployed in both models, we can see that increases in warm spells projected under SSP 245 are reduced. And so while the mean response of both models to both climate change and SAI is similar, we can still see some notable differences in future projections of warm spells between these two models, where, for instance, under SSP 245, warm spell event frequency is projected to increase more in UKESM1 than in CESM2. This likely occurs because UKESM1 has higher equilibrium climate sensitivity than CSM2, and so warms more over the same time period under the same emission scenario. And so to account for this discrepancy, we normalized the change in warm spell occurrence by the corresponding change in global mean temperature for the SSP 245 simulations. Next. And we can see that after normalization, shown here in the center column, that the relative magnitude of change in warm spell frequency is more similar between the two considered models. However, there are still differences in the spatial pattern of change. Next. And some of the largest differences in magnitude between these two models occurs over the regions highlighted here by the black boxes in the center column of this figure. And since these regions are over heavily vegetated tropical rainforests, we evaluated if there were differences between CESM2 and UKESM1 in how the vegetation is projected to respond to rising temperatures and greenhouse gas emissions over these areas. Next. And so carbon dioxide fertilization and stomatal closure describe 2 of the ways in which plants respond to anthropogenic climate change. Carbon dioxide fertilization describes the process where the rate of photosynthesis increases as carbon dioxide concentrations rise. Increased photosynthesis increases biomass production, which increases canopy transpiration and leads to a net cooling effect. And this is illustrated here on the left. On the other hand, stomatal closure, which is illustrated on the right, this process is where the pores in the leaves of plants close as atmospheric carbon dioxide concentration rise in order to limit exchanges into and out of the leaves. This decreases transpiration and leads to a net warming effect. And so these processes are both parameterized in the land models of CESM2 and UK-ESM1. And so to see how climate change might be impacting plant physiology in these models, we looked at future projections of leaf area index next. And so here we can see that under SSP 245, leaf area is projected to have large magnitude increases over tropical rainforests in CESM2 and small magnitude increases over these same regions in UK-ESM1. This agrees with the differences in future projections of warm spells between these two models, where CESM2 has small future projections. It projects small increases in warm spell occurrence over these regions, whereas UK-ESM projects large increases. Okay, next. And so to conclude, I showed that future increases in warm spell frequency are reduced when SAI is deployed in these models, and I noted that there are distinct differences in future projections of warm spells between CESM2 and UK-ESM1 that might be due to differences in the spatial pattern and magnitude of warming and differences in the plant physiological response to increasing atmospheric carbon dioxide concentrations over tropical rainforest. So yeah, finally, just want to mention that this work was recently published in Frontiers in Climate. So thank you.
Thank you very much, and sorry for some hiccup with the slides earlier. So we go to the next presentation now. This is from Jim Hurl, assessing the impact of solar climate intervention on hazardous convective weather over the continuous United States. Jim, please go ahead.
Great, thank you very much, Simona. And I'd like to begin by thanking the organizers of this virtual workshop. It's really great that you're doing this. I know it requires a lot of work, so thank you. I want to start off by acknowledging my co-PIs on this work, in particular Lighthouse Sun, who is the lead PI of a proposal we submitted to NOAA to support this work. Also Kristen Rasmussen here at Colorado State, who's an expert in mesoscale meteorology, and Ben Kravitz at Indiana University, who's an expert in SAI. Next slide, please. So thinking about how climate change as well as SAI might impact hazardous convective weather is motivated in part by a slide like this, which shows the time evolution of billion-dollar disaster events from 1980 through 2024. This is data from NOAA. And in particular, in response, you see an overall increasing trend, but if you focus on the green bars, which are related to billion-dollar disasters due to severe storms. Those are storms that produce hail and tornadoes and high winds. You see a very significant increase in these types of storms. And this is consistent with what our current generation of climate models indicate, which show that historical changes in climate, because of greenhouse gas forcing, the large-scale environmental conditions are really supporting an increase in perhaps the frequency and intensity of severe weather, in particular over the United States. And this was noted with high confidence by IPCC. Next slide, please. So we've done some work along these lines here at Colorado State. This is a figure from a paper that was published a little more than a year ago by one of my PhD students, Megan Franke, in which she used a large ensemble from the Community Earth System model to examine the time evolution of the forced responses represented by the ensemble mean in large-scale convective environmental parameters. She focused on the eastern United States from the period 1870 to 2100, looked at parameters such as convective available potential energy, convective inhibition, wind shear, and the like. I don't have time to define all of these parameters, but convective available potential energy, for instance, is really a measure of atmospheric instability that promotes cloud formation and thunderstorm development. The salient point is that the time evolution of these convective parameters suggests that indeed convective environments over the eastern United States have become more favorable for severe weather, in agreement with the observations that I just showed on the previous slide. with, very interestingly, the forced changes due to climate change becoming really clear relative to the internal variability after about 1990, and also indicate that conditions may be more favorable, even more favorable for severe weather in the future. Next slide, please. You just heard from Ivy, who's another PhD student in my group, and she looked at the evolution of these same parameters in the ARISE simulations that she just explained, where climate change follows the SSP 245 scenario with stratospheric aerosol injection introduced in 2035 to maintain global temperatures at 1.5 above the pre-industrial average. And in her study, she found comparable results to Megan's paper in terms of climate change. But what Ivy looked at were the ARISE simulations with stratospheric aerosol injection and found, as you can see in the lower panel, the lower row of figures, that future changes in convective indices were considerably smaller, as you might expect from thermodynamic considerations alone. Next slide, please. So as a next step, we'd like to move beyond just looking at changes in large-scale environmental conditions that really can only serve as proxies for severe weather. In particular, we wanted to construct some model simulations that find enough spatial scales to actually resolve mesoscale weather systems, which is really critical for understanding the physical mechanisms that may result in a changed convective population in some future climate. To do this, we use the WRF model, the Weather Research and Forecasting Model, which is a very widely used NWP model. And we ran simulations at 4-kilometer spatial resolution, forced at the boundaries by ERA5 data, to look at specific severe weather events over 2 time periods, March through August 2011, and October 2022 through June of 2024. Next slide, please. And the next slide is just to give an indication of the types of billion-dollar disasters that are covered by these WRF simulations. For instance, severe storms, the focus of today's talk, we have 45 samples of very significant severe storms that occur over these simulated time periods. Next slide, please. So the goal is to have these severe weather events and ask the question, how might those severe weather events change in some future climate, a future warmer climate? And to do this, we use the well-established pseudo-global warming approach, where the initial and the boundary conditions of the WRF model are modified based on projected future climate change signals from a global climate model. Again, in our case, utilizing the CESM. Hit the advance one more time. So what was truly novel about our approach, however, is that we also designed what we call a pseudo SAI run by once again adding the climate deltas for the same fields from the CSM simulations, but from simulations that include stratospheric aerosol injection, in particular from the GLENS and the ARISE scenarios that have been run in recent years. And in addition to those climate deltas, we not only increased greenhouse gas concentrations to the 2060s, which is the period that we're examining in the future, but we also added the aerosol optical depth changes from SAI to account for the reduction in downward shortwave radiation. Next slide, please. So to illustrate the success of our approach in terms of changes in surface clear sky shortwave downward shortwave radiation, what I show here in the panel on the left in the top row are reductions in the downward shortwave radiation anomalies for the 2060s relative to the current climate. For the ARISE SAI and GLENS SAI simulations performed with CSM in the top row in the left, and from our high-resolution WRF simulations in the lower panel. And I think you can see that we've succeeded in accurately capturing the CSM simulated downward reductions in downward shortwave radiation. And on the right is the same, just area averaged over the eastern domain of the United States. And if you're not familiar with GLENS versus ARISE, just note that the aerosol forcing is much stronger in GLENS as it's trying to offset the warming from an RCP 8.5 scenario. Next slide, please. As a final check in this methodology, in this figure, what we're showing are vertical profiles of March through August 2011 temperature anomalies averaged over the eastern US. And the main thing to note is the features in the CSM simulations indicated by the dashed lines such as the warming of the troposphere and the cooling of the stratosphere in response to increased greenhouse gases, and the warming of the lower stratosphere and relative cooling of the troposphere in the SAI runs, shown on the right, are well produced in the WRF simulations. So basically, this is giving us confidence that our pseudo-global warming and pseudo-SAI simulations can be used to examine the potential future impacts of both climate change and SAI on mesoscale weather events. Next
You have
slide,
2 more
please.
minutes about.
Yep. So to conclude, I just want to conclude with one brief example. This is from Bali Summers, who's a master's student in my group, and she examined the super tornado outbreak that occurred over a 3-day period in April of 2011, as shown in the upper left panel. This outbreak was one of the largest and deadliest tornado events in U.S. history. Advance, please. And what you basically see is that the WRF model simulates the mesoscale features of this outbreak very well. And here I only show daily average total precipitation fields for each day of the event. And you can see that the WRF model pretty faithfully reproduces this event. So next slide, my next to last. So her paper is about to be submitted for publication, and it details many aspects of this case study, including how well WRF simulates the observed dynamics of the storms and changes in the types of convection that occur. But because of time here, I only show histograms of 4 variables: precipitable water, rainfall rate, maximum updraft speeds, and 40+ dBz radar echoes, which serve as an indicator of potential for heavy precipitation and severe weather. And the populations of all 4 variables show an increase from present day in the probability density of high values in the PGW simulations. But in the SAI simulations, populations are much closer to those of present day. So the next slide is my final slide. I won't speak to it. It's just a summary and some next steps. And I guess the thing that I really want to share with this group is that if you're interested in these runs, we're happy to talk with you about getting access to the data. So thank you very much.
Thank you very much, Jim. Very great. A lot of work from your group, and good to see that. The next speaker will be Marie Tai, and she will talk about exploring the effects of deployment targets on extreme precipitation and temperature. Marie, are you ready? Please unmute and go ahead.
Hi, thank you. I'd just like to thank you, my collaborator on this work, Kwesi Kwagrain. We have a paper that's in preparation, and also other collaborators who contributed to the work over the last few years, including Jager Richter, Katie Dagan, Simona Dilmers, Matthew Henry, James Stone, Lauren Landrum, and Julie Maldonado. But anything that I present here is my own opinions and not a reflection of them or NCAR. I also have QR codes embedded for the publications and data that I reference. Next slide, please. So just to motivate the talk, the way that extreme weather is really how people, is what resonates with people, and it's what has people talking about climate change, how they understand it, and it's what they then talk to their politicians and ask and vote on as well too. And so these are the things that have the greatest impacts and are most important to consider. Next slide, please. But extremes are highly contextual and can vary with the seasons and from location to location. So a certain amount of heavy rain can be what actually drives agriculture, but excesses of heavy rain can then lead to devastating floods. Similarly, long, warm, dry spells can help grow crops, but it can also, in the wrong locations or in the wrong seasonal context, can lead to drought conditions or even potential for fire. Next slide, please. So Jim has already mentioned the Glens ensemble, and we used this motivation of looking at extreme temperature and precipitation to understand what the impacts might be in various different regions. The box plots down the bottom left look at measures of the wettest day per year and the number of heavy rain days above 10 millimeters per day for different regions across the globe using the AR6 regions. The red are the RCP 8.5 back emissions alone. The grey boxes are those from the control climate, or the sort of the climate that we were seeking to maintain. And then the blue are the GLENS results. And really what I want to highlight here is that there is a lot of heterogeneity across the regions, that where SAI may improve or may maintain the current climate in some places, but in places like Central Africa and Western Africa, it could actually reduce the number of heavy rain days in a region that is agriculturally dominated. And that even within those regions, there is a high degree of heterogeneity, with increases in the annual wettest day projected in some places and considerable decreases in other locations, even within the same region, related to changes in the intertropical convergence zone. Next slide, please. So looking at that same measure, the annual wettest day per year, within the next set of simulations that were also mentioned by Jim and by Ivy, the ARISE simulations. And so on the top left, we have the results from the ARISE, the UK ESM1, with a target temperature of 1.5 degrees, and on the top right is CESM2 at the same target. And what I'd like to flag here is that there are differences between the two models, even though they are trying to target the same global mean temperature. There are some regions that are projected to dry within UK ESM versus increasing in the most intense rainfall in CESM2, just because of those model structural differences. And then in the bottom row is the two more simulations from using CESM2, but looking at different targets. So with a temperature threshold of 1 degree Celsius instead of 1.5 degrees, just a little bit cooler on the bottom left, and on the bottom right at 1.5 degrees again, but delaying the start date until 2045. And again, there are differences between the models and between the results. You don't necessarily achieve the same reduction in extreme precipitations. There are some projected increases, in fact, and as well as decreases. Just by waiting for 10 years, there are projected increases by trying to overcool, and there are associated changes in where the intertropical convergence zone lies, and various other measures of extremes.
Sorry, you're out of time about. Can you wrap up?
So next slide, I just wanted to conclude by saying that it's very important that we maintain, that we look at many, many different models, and that people who have the opportunity to be analyzing results, I would highly encourage you to also to look at the extremes, as that is something that really resonates with what people need for decision-making contexts. And thank you very much.
Thank you very much. We'll go right to the next talk, which is Cameron Dong, distinguishing between the short-term climate responses to unilateral stratospheric aerosol injection latitudes with artificial intelligence. Thank you. Go ahead, please.
Okay. Hi, everyone. Thanks for having me. I'm a postdoctoral researcher at Colorado State, and today I'm just going to present some work that was recently submitted to JGR Atmospheres. Next slide. So the main question I'm trying to answer this work is, can we distinguish between the climate impacts associated with different injection locations, or rather latitudes, on seasonal to annual timeframes? So there's been a lot of work looking at the kind of long-term average response of the atmosphere and the surface to different injection latitudes. However, here I'm more interested in thinking, can we differentiate those differences amid a backdrop of interannual variance in seasonal to annual composites? The data I used to perform this analysis is using experiments that were run by one of my co-authors, Charlotte, as part of her PhD thesis, which are these atmospheric simulations that were run for about 1,600 years, where there are continuous unilateral injections on 2-year cycles, where the location shown by the different dots in this plot and the rate, ranging from 1 to 16 teragrams per year, are changed on January 1st every 2 years. Next slide. To kind of quantify this distinguishability and look at what are the kind of important regional differences in the climate responses, we use this explainable artificial intelligence methodology. First, we have as input seasonal or annual composites of temperature or precipitation anomalies over land. These are fed into a relatively simple neural network, which outputs the probability that for each of those composites, injections occurred at each of the potential latitudes. Additionally, the explainable part is where we output using gradient times input, these distinctive patterns that show what regions did the neural network focus on in order to identify the injection latitude. So in general, the regions with the green and darker green show the important regions of cooling or warming or precipitation that were important for that or strongly associated with that particular injection latitude. Next slide. First, just as a quantification of the distinguishability, we use the network accuracy, which is shown on the y-axis of both of these plots for land temperature and land precipitation. Just like a quick overview of some of the main takeaways is that large injections, which we identify as 8 or 16 teragrams per year, which is rather large, lead to much more distinguishable impacts, as you would expect, compared to the small injections, which we define in the scope of this study as 1 or 4 teragrams per year. And that's shown by the difference between the dark blue bars versus the light blue bars. There are also significant differences based on season, so boreal summer versus boreal winter, which we'll discuss later in this talk. And in particular, temperature, which is directly affected by the radiative forcing of SAI, has bigger differences between injection latitude that are more identifiable by the neural network than for precipitation. Next slide, please. So here, just an example of how the explainable AI method kind of works for 2-meter temperature over land. We have some plots where the left column shows the temperature anomalies and the right column shows our explainable AI output. In the top row, we show an injection at 30 degrees north, where you get really broad cooling over much of the northern hemisphere. However, the network is really able to focus in on certain regions within that cooling that are really unique or more strongly associated with injections at 30 degrees north. For the middle row, we have injections at 15 degrees north, and that is really associated with a very similar overall cooling pattern. However, the network is able to focus on like kind of those subtle differences between the climate response to the different injection latitudes to identify, where was the injection during that time period. And then the final row just shows an example for a southern hemisphere injection where the network focuses on the southern hemisphere mid-latitude cooling. Next slide. Okay, I won't really discuss this for the sake of time, but we can also do a similar thing with precipitation and showing how the ITCZ really shifts north and south along with the injection latitude. Next slide. Okay, and then lastly, I just want to talk a little bit about the seasonal variation of this distinguishability on the seasonal to annual timescales. So when we look at 30 degrees north injections during boreal winter versus boreal summer, most of the signal is dominated by, the northern hemisphere landmass, and there's similar raw temperature anomalies during both of these seasons for the same injection latitude. However, there's a lot more interannual variance in the winter hemisphere than there is in the summer, which means that this larger winter annual variance really masks or more effectively masks the signal from the SAI. So the network's able to learn these cooling patterns and distinguish the different injection latitudes in the summer hemisphere, but not necessarily in the winter. Next slide. Lastly, I'll just leave some of the key points and takeaways. Thanks for having me here for this talk, and thanks to the organizers for all their work in putting this together.
Thank you. I'll give it a couple minutes for looking at this. And now we go to the next talk, which is by by Tevin Singh Kapoor, Rethinking Alumina for Stratospheric Aerosol Injection, New Insight into Shortwave Absorption. Okay, are you online? Please unmute and go ahead.
Yes, hi. Hi, everyone. I'm Tevin Singh Kapoor, a postdoctoral researcher at Washington University in St. Louis. And I'll be presenting some of our group's research on the optical properties of candidate aerosol species for stratospheric aerosol injection. Specifically, this presentation is on alumina. Next slide, please. So if we look at the ideal or the desired properties of SAI particles, they would be that they should be strongly scattering and absorb negligibly. And this is characterized by the refractive index of these particles, which is a complex number, has a real part which determines the scattering, and the imaginary part, which we call K, which determines the absorption. And there are other properties as well, like these particles should have low densities, well understood surface chemistry at stratospheric conditions, and a low environmental toxicity. But this presentation will focus on the first 2 points on the optical properties, specifically the absorption, because along with the particle size and particle shape, which are fed into the climate models to understand their SAI efficacy, they determine how these particles would interact with solar radiation as well as the outgoing log wave radiation. And based on some of the calculations right now, it looks like alumina is one of the promising candidates. Next slide, please. If you look at what the optical properties that our present understanding shows for alumina, it's shown in the graph here, where on the x-axis we have the wavelength, and on the y we have the imaginary refractive index. And the current data set is from a handbook by Tropf and Thomas, which compiled previous literature on the optical properties of ideal alumina crystals across the wavelengths. But you see that there is data available in the ultraviolet range as well as the infrared range, but the data in the middle where we have a lot of the solar radiation is missing. And previous studies have tried to interpolate this absorption using theoretical models to get a refractive index of about 10 to the power of -7. But these are caveated by the fact that these refractive indices are for ideal particles. And if we consider practical materials, they might contain impurities or defects or other imperfections which could lead to enhanced absorptions. And that there are lab studies which would be needed to further understand their optical properties better. Next slide, please. So this brings us to the problem statement that we have at hand, which is that alumina is proposed as one of the candidates for stratospheric aerosol injection. Along with that, they're also being emitted from spacecraft launches and re-entries. But if we look at these particles carefully, they could be ideal crystals of alumina, or they could have some kind of defects. And whereas an ideal crystal would have a large band gap, which means it would absorb negligibly based on some of the present predictions, some practical materials could have defect states or mid-band gap energy states, which could introduce absorption in the shortwave. So we probe this absorption, which has not been measured so far, using 2 techniques, photoacoustic spectrometry and electron energy loss spectroscopy. Next slide, please. Photoacoustic spectrometry is an in situ measurement technique where we hit these particles with pulsed laser light, and that triggers sound waves, which we detect as the absorption of by the material. And together with integrating nephelometry, we combine these 2 techniques to measure the total absorption and scattering coefficients of these particles in situ in the lab. And we have 5 of these in the lab right now, which we build in-house and use for our experiments. Next slide, please. The experimental setup looks a bit like this. We have a dust generator adapted from a previous study. So we procure these particles which are commercially available. We put them into the dust generator, we aerosolize them, have them mix them well in a buffer chamber, and then pass them through our instruments to measure the absorption and scattering coefficients. Also, we measure the particle number size distributions, and then together size distribution and the absorption and scattering measurements, we invert the refractive index using mean theory. And we also collect these particles on electron microscopic grids. Next slide, please. And we put these particles under an electron microscope where we bombard a spot on some of the particles with an electron beam of a known amount of energy, and then that energy gets slightly attenuated by the particle, and we get an energy loss signal like the one shown on the right over here. The electron energy loss signal has a high energy loss region, which gives us information about the chemistry, the oxidation state, and so on. What's interesting to us is the low loss energy region, which gives information about the vibrational phonons, plasmons, and optical excitations, from which we get the fundamental dielectric constant, from which we can infer the refractive index. Next slide, please. So this is what the refractive index now looks like. The measurements by Troff and Thomas, the handbook back in 1997, are shown in the black line or the black scatter markers over there. And you see that at the band gap edge, there's a sharp decline, which is what ideal crystals should probably behave like. And if we compare that with what we have measured, for example, using the electron energy loss spectroscopy, we see that there is a sharp decline at the band gap edge. Please note that the y-axis is in a log scale, but that decline is slightly arrested by what we are attributing to oxygen vacancy defects within the crystal material, which are actually thermodynamically favorable when these particles are being produced. And after that absorption ridge, there is a decline, and the scatter markers shown in green, they are basically what was measured by the photoacoustic spectrometers at 5 different wavelengths. And you see that both the measurement techniques give us an equalish value. They are related to, they are pretty close to each other. And using these refractive indices or the photoacoustic spectrometers, we are able to, we use an Urbach energy fit to get a continuous information on the optical properties, which we can use in the future to model the climate impacts. Next slide, please.
We have two minutes left.
Mm-hmm. To just give a quick feeling of what the optical properties, what kind of consequences they may have in terms of the radiative forcing, we use the method developed by Ross and Schaefer, which gives us a first-order estimate of the instantaneous radiative forcing that these particles would have if emitted to the stratosphere across a range of alumina burdens, ranging from spacecraft emissions that I spoke of earlier to much higher concentrations that we would need for SAI-based scenarios. The red line shows the radiative forcing, and the shaded region basically shows the kind of uncertainties that we can have from basically the measurement uncertainties in the refractive index. There's a linearly increasing trend, and if we compare that to the refractive indices which were reported previously and used presently by the models, we see that there is a 3 to 4 order of magnitude increase in the absorption, which is kind of being underpredicted. Of course, there are other studies which entirely neglect the absorption, so k equal to 0 would be a flat line at the bottom. So this heating would supplement any long wave heating that alumina also has. And more crucially, it would offset up to 10% of the shortwave scattering that these particles are currently modeled or currently believed to have. So any calculations of the SAI efficacy and payload calculations, etc., would need to be slightly revisited in light of these findings. Next slide, please. With that, I just come to my summary, and what we've basically done is we've developed a method to measure these weak absorption signals that a candidate SAI species have, and these would help in the future to understand a little more accurately to understand what the SAI efficacy would be, and some calculations may need to be revisited. And these findings that I presented today are available on arXiv, and the study is under review. And if you'd like to know more, you can always feel free to reach out to us. Thank you for your attention, and I thank the organizers for this opportunity.
Thank you very much. We will have our last talk now by Eva Bednarz, And just before I read the title, please remember to put in your questions in the Q&A for the discussion afterwards for all these presentations. So Eva will present on SAI impacts on stratospheric ozone, large-scale circulation, stratosphere-troposphere coupling and links with surface climate, understanding processes and narrowing uncertainties. Go ahead, Eva.
Thank you, and sorry for the mouthful of a title. So yes, I'd like to talk a little bit about basically narrowing uncertainties in SAI impacts on the atmosphere and climate, and what we can do, and that in order to do that, we need to better understand the processes driving those uncertainties and those climate impacts. Next, please. Next, yes, thank you. So we know that stratospheric aerosols reflect solar radiation, but that doesn't just cancel greenhouse gas-induced warming. We know that aerosols also absorb some of the shortwave and longwave radiation, giving a warming in the lowest stratosphere, and that can then have a knock-on effect on the circulation. And we know that aerosols also provide active surfaces on which heterogeneous reactions can occur, and these in turn can change concentration of species in the atmosphere that are important, for instance, ozone. And importantly, there are still large uncertainties in most of those processes under SAI, and these uncertainties in turn contribute to the relatively large uncertainties in our projections of potential SAI impacts. Next, please. So for instance, we know that SAI impacts large-scale circulation. So the warming in the tropical lower stratosphere, this changes meridional temperature gradients, giving you strengthening of stratospheric jets in both hemisphere. And because stratospheric circulation changes doesn't just matter in the stratosphere, but in part of the year, those stratospheric anomalies can actually propagate down to the troposphere and affect surface climate. And this is particularly the case in the northern hemisphere high latitudes, not just in the SAI context, but more broadly. And that typically occurs during winter, as I show on the right-hand side plot. Next, please. However, SAI and its impacts is not just one thing, but the response heavily depends on the details of SAI realization. I know there's another session tomorrow about that. So here I have 4 SAI simulations that achieve roughly the same level of global mean surface cooling, but they do so via different combinations of injection locations, so what's commonly referred to as SAI strategy. And we see that this different SAI strategy, they are associated with very different magnitude of stratospheric responses. And those both the tropical lower stratospheric heating and then changes in stratospheric polar vortex strengths. And those differences would then have a knock-on effect on surface responses we simulate under SAI. Next, please. So SAI can also impact ozone, and it can do so via a number of processes, both chemical processes, so heterogeneous halogen activation and sulfate aerosols, but also dynamical processes, so any changes in stratospheric circulation and transport. And the ramification of that is that the final SAI-induced ozone response is complex, and it reflects SAI impacts on all of those processes. So I have it exemplified on the left-hand side. This is like example SAI ozone response to SAI occurring at the equator. And we look at it, we basically see a mosaic of both positive and negative ozone changes, depending on the region of the atmosphere you're looking at. And then on the right-hand side, I got the vertically integrated total ozone column changes in those 4 different SAI strategies. And again, we see that even though those SAI strategies give you roughly similar level of surface cooling, they can give you very different ozone responses. And this is because different processes matter more in some SAI strategies, and some other processes can matter more in the other strategies. And next, please. So that was complicated. That was just the results of one model, and we all know that models differ, and this was already complicated enough. So I want to highlight some of the intermodal uncertainties using this new GeoMap experiment, the G6 1.5K SAI experiment. Very briefly, it follows the middle-of-the-road SSP2 4.5 greenhouse gas scenario, and it includes SO2 injection in the subtropical lower stratosphere at 30 degrees north and south. And currently there are 4 models that so far participated in this experiment. I only have data for 3 of them, but I hope to include the 4th one, the E3SM, shortly. Next, please. So this is a similar plot that I showed you before. Yes, thank you. It shows the magnitude of lower stratospheric heating on the left, the magnitude of Antarctic polar vortex strengthening in the middle, and then magnitude of Antarctic ozone depletion in the right-hand side. So this is for CSM2 and how the response depends on the details of SAI strategy. And the slight difference is that I now normalize the response, the stratospheric response, with the
associated change in the global mean surface cooling. So these are basically stratospheric changes expressed as a 1 Kelvin global mean surface cooling. Next slide, please. So we can now add the new geomap experiments to this plot. So those experiments, remember, they injected 30 degrees north and south. So I showed them in green in here. And we see immediately the bad news is that we see that intermodal uncertainties can actually be as large as the uncertainty coming from the choice of strategy within the single model. Now that was bad news. The good news is that it's not just completely random, but there is generally a correlation between the three responses, so that the models that show larger low stratospheric heating, they also show larger Antarctic polar vortex strengthening and the ozone depletion. Now, next slide, please. This was the response over 2045 to 2064, so like 10 to 30 years under SAI started. Now, if you look at the response later in the century, on the left-hand side, the normalized lowest stratospheric heating response is very similar, which is good because this is what we would expect. However, for the wind and ozone response in the stratosphere, so the middle and central panel, we see there's a clear systematic reduction in the magnitude of the response as we go later into the century. So for ozone, this is because SAI can have a much larger effect on stratospheric ozone earlier in the century when background halogen concentrations are still higher. But the fact it's not just the ozone response that is sensitive to the timing of SAI, but it's also the wind response. This basically illustrates that the ozone response to SAI can play an important role in modulating the dynamical response to SAI, and it can also contribute to some of the intermodal spread in the dynamical responses we simulate. Next, please. And just to say, for anyone interested in SAI impacts on ozone and on the stratosphere more broadly, the upcoming WMO ozone assessment in 2026 will once again have a chapter on the SAI impacts. And I'm one of the co-authors that contribute to the assessment. And please, next, please. And just to summarize, I try to give you a very brief argument why, in order to understand uncertainties in SAI impacts on the atmosphere and climate, we need to better understand the processes that drive those impacts and those uncertainties. And I give you an example how the response can actually be strongly dependent on the details of SAI realization, and how there are still significant intermodal uncertainties that needs to be addressed. However, it's not just bad news. There's currently a lot of work going from different centers looking at narrowing some of those uncertainties. And I gave you example, it's not just we need both sensitivity simulations with single models and intermodal comparison studies, as well as more broadly comparison with observations, but this is not part of my talk. And yeah, that's about it. Thank you for having me here.
Thank you very much, Eva, and thank you to all the speakers. This was a great session, very diverse, going from the whole stratosphere. Kind of Eva summarized it all up and even into aluminum. So we do not have any questions right now in the Q&A. However, there's already one question that is in the chat that some participants may not see. I will read it. So it's on alumina and the presentation, which has surf health consequences. And has this been taken into account? So Taveen Singh, maybe can you comment on this, or others that are potentially be here in the panel? Do you want to comment on this?
Yeah, I suppose I'm not strictly aware of whether there have been studies or considerations on this. I think it is toxic. It has an acute toxicity, so prolonged exposure could be a problem, but sorry, doesn't focus on that. Sorry.
If anybody else wants to chime in, please raise your hand in terms of health. But that is certainly an important question. How much do solid aerosols impact our health? And definitely not. Oh, I'm not aware that that has been studied in detail. So yeah, we do not have any Q&A questions, but please, everybody who is here can please raise a question. And we already have a hand up. This is from Ron. Please go ahead and.
Yeah, thank you, Simone. I did put something in the chat, but I guess it didn't go through. I just had a question for Cameron Dung. regarding how his results compare to the results of Brody et al. In 2025, who looked at a kind of multi-objective strategies for SAI deployment, across different latitudes, all jointly to target multi-objectives. I don't know if you're aware of that, but I found it extremely interesting and important kind of work.
Oh, thanks for your question. I don't remember exactly the results of Brody at all. I think I've seen it, but I don't quite remember exactly. But I think in terms of like the multi point injections, like multi latitude, where they like inject like in both hemispheres, effects are like more, yeah. Yeah, I think compared to like the single, so in our experiments, I'm mostly looking at like the single point ones where it leads to a lot of more like or interhemispheric asymmetries that I think are may lead to like be more distinguishable in that sense for our work, but where the goal, I guess, for like the multi-point injections, multiple latitudes is the goal is to like kind of like cancel out some of those effects, especially for precipitation. That might be different than what we see in our kind of single point simulations.
So just if I could just follow up real quick. I mean, I'm not a climate scientist myself, but he uses Daniele and Doug could probably speak to this better than I could, but it's a degrees of freedom kind of analysis on both. So anyway, I'll stop there. I think it would be interesting to look at those differences.
Yeah, that's a good comment. And Danielle, do you want to add quickly?
Yeah, I can say that Cameron, actually, those simulations, we have multiple simulations of single point injections also done with CSM, so I was a bit surprised. And you should definitely take a look at those results and try to compare what you obtained through your work with the ones before in terms of looking at single point injections rather than we also have those rather than just the hemispherically balanced ones.
Yeah,
Okay,
great.
yeah, thanks for the suggestion.
Okay, good. Yeah, more work to do, more comparison as always. Yeah, so there's a question from for Ivy in the chat, and in terms of heat spells, in the increase and decrease of heat spells from climate change and SAI over time, is this change a trend over the years or a shift? How stable is it? Ivy, do you want to respond to this? I think you did, but please repeat.
Yeah, sure. I can kind of just discuss my answer in words. Yeah, so the figures that I was showing was looking at the difference in the annual mean warm spell occurrence over the 2060 to 2069 period. Like the change for that period, and then I subtracted the 2020 to 2039 annual mean warm spell occurrence. So I believe this would be the shift in warm spell occurrence over time. It wasn't like a increase in warm spells per year, for example. But yeah, as far as how stable is it, I think I might need a little bit of clarification on that part.
Okay, thank you. I want to point out that there will be a longer discussion, the same as for the detection and monitoring, also on the impacts. We do have only 3 more minutes left. If there is still some detailed questions, we can go for that. I don't think we want to go into the bigger questions at the moment. Any other more detailed questions? Something to think about maybe is also really thinking about Eva's talk, I think, and there's a question by James Fleming, but I had a question for Eva also, what you think about all the various possibilities for injections and impacts. How will that also reflect on the previous talks that we have seen for surface climate? how much differences do you expect? With differences, many people just choose one strategy and one
Yeah, you
model.
definitely have to explore different strategies because it's the main point. Like the SAI is going to have different impacts depending on the realization. So while single model studies are important, single scenario studies are important for impacts, one need to put each incremental advance in knowledge into wider space, because it's not like a greenhouse gas problem that the more greenhouse gases there is, the bigger the impact. It's a much complicated problem. And yes, especially with the single point injection, we've seen that many of the disadvantages of the single point injections goes away if you actually do more clever stuff when you combine the injection locations.
Thanks. That makes sense. Maybe the last question now. Do you want to go ahead, Jim? We can't hear you. Can you please unmute you and start over?
I had a question for Dr. Kapoor about the toxic characteristics of alumina, which is carborundum or aluminum oxide.
Yeah, go
Yes.
ahead.
Yes, I'm sorry, I don't have an answer to that right now. That's not something we've looked at so far. But as I understand, it's acutely toxic and prolonged exposure would be an issue.
Okay.
Yeah.
Okay, thank you. And John Paul, did you have your hand up? No? Okay, now Frank has his hand up. Frank, you want to comment?
I will just briefly comment that, of course, there are incredibly large amounts of wind-blown mineral dust at Earth's surface. So among those is alumina. Of course, it's just one component. And so the way to look at it is how much are you adding to the background burden of similar materials that you find in the troposphere. And that doesn't mean that it's good to inhale wind-blown mineral dust. But the point is there are vast amounts of that, much larger scales than anything you're talking about here that already are blown around. That doesn't mean it shouldn't be studied, but just to keep in mind that that is the case.
Okay, that was a great concluding remark on that question. And with that, we conclude the session. We have a mini break and we'll see you all in 3 minutes at 40 minutes after the hour. Thank you.
Liwa, can you try going back and forth because I see the whole, yeah, okay, perfect, thank you. Okay, hope you had some rest, everyone, and we're here for the final session of the day. So for this last session, we'll talk about the ethical aspects of studying and testing SAI. And our first speaker is James Fleming. James, please.
Yeah, thank you for having me in the conference. I'm really enjoying the up-to-date work on modeling and measuring stratospheric aerosols. I was in the 2006 NASA Ames workshop on managing solar radiation. And this was just a cartoon I cobbled together after that meeting. We've come quite a long way from there, where this was just after Paul Crutzon's modest proposal published in Climatic Change. What I'd like to do now is review the legal precedents, current challenges, and pressing needs, and basically argue that history matters, and we should take a look at the longer perspective on especially deployment of SAI. And I'm certainly in support of research, but I think the deployment needs governance. Next slide. Okay, and I draw an analogy to the Asilomar Conference on recombinant DNA in 1975, and that was aimed to shape the governance of modern biotechnology. And the take-home of this was that the scientists were emphasizing voluntary guidelines created by themselves, emphasizing containment and risk assessment, and they were trying to avoid formal government regulation. There is some regulation, but it's not very strong now. And as of now, our DNA has no organized global governance. Next slide. I'm sorry, I keep trying to move my own slides. The Asilomar 2010, which was decades later, was held for the geoengineering, and the focus of that was on governance. Next slide. So I was there too, and it aimed at shaping the governance of climate intervention technologies. I think the conference succeeded in initiating a broad and somewhat interdisciplinary dialogue among experts to provide guidance for scientific community. And it sought to stimulate discussions, which it certainly has, although as of 2025, there's no global governance of SAI, and there's a lot of speculation about how that might be formed. Next. There was pushback after the Asilomar Geoengineering Conference, and some of this pushback was, again, about scientists trying to self-regulate their activities, and the voluntary guidelines was simply not strong enough. And it seemed that self-regulation might be aimed at avoiding stronger external regulation. So next, please. I want to give a real deep precedent. I'm a historian of science, of training in atmospheric science, but Sir Francis Bacon, the acknowledged founder of experimental science, talked about increasing knowledge that would be beneficial for the common good. It would be good for all fields, and it would be applied to all fields, including meteorology and climatology. And for several centuries now, planners, politicians, scientists, and specifically soldiers have proposed schemes for manipulating weather and climate. And it's usually for military or commercial purposes. But I want to bring your attention to The New Atlantis, really a landmark essay by Francis Bacon, in which the scientists in Solomon's House practice both observation and manipulation of the weather. They're trying new experiments as they themselves think good. That is, they manipulate nature without further review or oversight, a task that would require perfect virtue and judgment by the experimentalists. So I think this is a long-term issue with modern science, and Bacon was one of the founders of the experimental method. So this, such as themselves think good, is not good enough. Next, please. So at Asilomar, I had just finished a book called Fixing the Sky, and that was a history of weather and climate, attempts for weather and climate control up to that date. And I heard statements from the podium that we don't have a history of, it was called geoengineering in that conference. And I said, well, I basically got up and I said, yes, we do. things are moving too quickly, so we don't have the luxury of looking at history. This is another keynote speaker. And I said, you must take the time. It could take you 4 or 5 hours to take a brief review of the history. And another statement, we are the first generation to think about these things. And I think history says otherwise. And everything seems unprecedented if you don't study history. Next, please. So there are some precedents, and I wanted to talk about those. Following the experimental detonation of H-bombs in outer space, this was in 1962, Britain's Astronomer Royal issued a statement that no government has the right to change the environment in any significant way without prior international study and agreement. And that led to the Limited Nuclear Test Ban Treaty, where no country can take action that could cause a major disturbance to the natural environment of the Earth without prior consultation with other countries. And this was a really big deal because the magnetosphere had just recently been discovered, and it recently had been disrupted by Project Starfish and the H-bombs. There's another precedent following widespread cloud seeding, spelled wrong, in Vietnam. In 1978, the NMOD UN treaty was enacted, prohibiting environmental modification that changed through deliberate manipulation of natural processes, the dynamics, composition, or structure of the Earth, including its biota, lithosphere, hydrosphere, and atmosphere, or of outer space. And this was in the wake of environmental warfare that was going on in Vietnam, and the UN brought together a treaty taking a very close look at that. The NMOD treaty is still in force, although it's never been actualized. Next slide. And so in governing SAI, fast forward now to post-Silomar, the Royal Society established a solar radiation management governance initiative. Possibly all of you are aware of that. And it's regulating, it advised regulating it as a public good and had certain principles of full participation, transparency, independent assessment. And they reiterated the Oxford principles that it should be a public good, that the public should be involved, that international participation is required. And these kind of things led me to what I call the 3 I's. That is, geoengineering or climate intervention should be international, it should be interdisciplinary, and it should be intergenerational. And praise to the organizers of this meeting, but we only have a few people who are not from the developed North and West. I think there's 6 from the Southern tier. And there's only a few people who are truly interdisciplinary in the sense of history, humanities, public policy, social sciences. And I don't know how many intergenerational people there are. There's a few young students from Colorado State. So I think we have to do better with the 3 I's if we're going to talk about global governance. And currently there's, as I said already, there's no global regime for governing geoengineering. Next. There is literature. There's a book called Geoengineering Our Climate, Ethics, Politics, and Governance. And I give the citation there, 2019. There's also a recent article on solar radiation management, history of the governance and political milestones. I don't know if these people are involved in this meeting, but they say it's largely been, the whole conversation has largely been driven by scientists and actors from the global North, while the climate vulnerable communities have been left out, and they have the most to gain or lose. And so we need to do better again. And there's my 3 I's, the international dimension, the interdisciplinary dimension, and the intergenerational dimension. Next slide.
James, you have 1 minute left, please.
Yeah, this is my last slide.
Great.
Next to last. The recent developments include the Convention on Biological Diversity. They called for a moratorium on SRM, and the Montreal Protocol, trying to protect ozone. And the scientific advisors to the European Commission proposed a moratorium on large-scale experiments and deployments, and the African ministers and ministers from other countries are looking at non-use agreements. Final slide. And so the prospect is the UN Environmental Assembly, UNEA 7, will take place this December in Nairobi, Kenya. They have an initiative to look at solar geoengineering non-use agreement, which is a kind of a voluntary petition that's out there that recommends against public funding and outdoor experiments. And then in Congress in the US, there's the Clear Skies Act that seeks to impose federal ban with penalties on weather modification, including geoengineering. And again, I'll just end by saying this is an imaginary thing to govern, and there is no global governance, but it has to be international, intergenerational, and interdisciplinary. Thank you.
Thank you, James. Okay, next we have Professor Jenny Stevens. Jenny, are you okay? I can see
Yeah,
you.
I'm here.
So, yep.
Can
Please
I
take it
go?
away.
Okay.
Yes.
Great. Well, I think that was a great introduction. James Fleming's talk. Because I'm going to present from a climate justice perspective, which is prioritizing marginalized and vulnerable people and communities and households. And from that perspective, I think SAI is very dangerous, and there's no way to deploy it in a just and equitable way. So I think following on from mentions of the solar geoengineering non-use agreement, I think that it's very important obviously most of the people are working on SAI are physical scientists who are thinking about the technical details. But in fact, when you think bigger picture, zoom out and think about society-wide and the social consequences and the need for governance, but our complete inadequate, nowhere near governance structures that we have, and in fact, the current global governance is in the International Court of Law is not even Court of Justice is not even upholding any of the things that they've said that's why it is a fabrication to think that we could do this in a way that with some governance structures. Next slide, please. So again, I'm talking about from a climate justice perspective, and from a climate justice perspective, it really does not serve humanity well when we focus narrowly on climate change in isolation of everything else. Climate change is not the problem that needs a technical fix. It's actually a symptom of an extractive, exploitative economic and political system that is just concentrating wealth and power more and more. So a climate justice perspective focuses on power. And that is, I think, the most important thing, especially in this world that we're in right now, that we all need to really be focusing on. And SAI creates one more mechanism for the rich and powerful to control and manipulate everybody else. So next slide, please. So I think when you think about the injustices of SAI or solar geoengineering, it's really important to recognize, and there's been work I've co-authored this paper with Kevin Surprise that really just points out how this is a technical approach that concentrates wealth and power among those that already have wealth and power in the world. And as James just mentioned, it really is exclusive of so many people. And when indigenous or feminists try to resist and call out against the dangers of this, oftentimes people are just dismissed and disregarded. Next slide. When we think about the dangers, so not just the injustices, but actual danger to humanity, as some of the scientists earlier mentioned, the heterogeneity of deployment, especially with extremes, is so strong that there's no way for SAI ever to be deployed in a way that isn't dangerous to some. So and then in terms of geopolitics, obviously it concentrates geopolitical power. It's a human rights nightmare. And that's what others have said, not me necessarily, but the potential for devastating and unintended consequences of this is just huge. And as was mentioned earlier, it has huge potential to disrupt hydrologic systems, food systems, the monsoon patterns. And again, the risks of manipulating the Earth system in this way, and the fact that humans are even thinking that this could be a good idea to try to control the Earth systems in this way is really, really dangerous on so many levels. Not just the physical risks, but the governance and power and political power risks of it. Next slide. Another big danger and injustice, which we can see right in front of us, is all of the profit-seeking startups that are already taking people's money and making claims that they are cooling the Earth for them. You can give this company Make Sunsets hundreds of dollars, and then you can they will give you cooling credits that you can say offset your something else. Which there's no regulation for this. It's scientifically and politically and economically a scam, I would say, but it's happening. So this shows the danger, the injustices, the risks, the fact that these rich people are trying to make money off of this kind of a thing, I think is a real representative of the dangers and the injustices. Next slide. So I would just say that from my perspective, I study climate obstruction, which is denying, delaying, distracting, distorting, and deterring real transformative change is what we need to address the climate crisis and all the other crises, ecological crises that are going with it. And from that perspective, SAI is actually climate obstruction in a way, right? Because it provides this deterrence, a mechanism by which people are increasingly turning to and saying, oh, we can't do anything else, so let's do this. Or let's invest in this or let's study this. And it is deterring other more transformative actions. Next.
You have 1 minute left, Jenny.
Yeah, so I've also studied how higher education has been obstructing transformative climate action, and how this scientific technical focus on understanding technical fixes like SAI just reinforce this idea that scientists and higher education and all these researchers are promoting and legitimizing this very dangerous approach. Next slide. And I talk about this in my book, Climate Justice and the University, which is an open access book that in the research chapter talks quite a bit about geoengineering research and who's funding it and why, and how scientists and universities have kind of been captured by that. And there's also a lot of research that we've done showing how the fossil fuel industry has been investing in higher education and these kinds of climate techno fixes since the 1970s as part of their climate obstruction strategy to make sure they're not regulated and they can just keep making money and they can just keep extracting fossil fuels. Next slide. This is my final slide to just say what we really need is fossil fuel phase out. And almost none of our university research, climate and energy research centers are doing research on how to phase out fossil fuels globally. And that's actually what we need. And I hope and I trust that there'll be some shifts in our university and academic research to really focus on what we need for humanity in this very dangerous time that is just accelerating, again, with climate as only a symptom, but we really need to address the root cause and change our structures and systems so that the fossil fuel industry doesn't have so much power and that we phase out fossil fuels. So I will end there. Thank you.
Thank you, Jenny. Next, we have Ron Hyman.
Yes. Thank you, Daniele, and thank you for the conference organizers for inviting me to present this presentation. I would like to thank my co-authors who I was unable to put on my slides because I didn't have time for them to review it, but this is Mike McCracken and Gregory Slater. So First of all, let me just state that I don't know if this was I doubt that it was on purpose, but it's interesting that I come right after Jenny because my perspective is almost diametrically the opposite. Even though I must say I come from the left, I have been struggling with power. I spent decades as a progressive heterodox economist, which I still am. And my thinking is that we're just flat out of time. You know, if you have some other alternative to keep us from crossing calamitous tipping points, which will cause severe harm to you know, all over the world, especially in the global South, then I would like to hear them. But anyway, let me continue with my presentation. First of all, can I have the next slide, please? So let me just read the title. I'm sorry. SAI deployment and human civilization. The question is no longer if, but how, when, where, and whom. So first of all, how. Next slide, please. So this is will be very familiar to people. We advocate. I'm part of a group called the Healthy Planet Action Coalition that advocates cooling, removal, and cooling, emissions reduction, carbon removal as the climate triad. We need to do all three as soon as possible. But really, in order to have time to get the job done, the fundamental job, I agree with you know, previous speakers on this, the fundamental job is to get the greenhouse gases out of the atmosphere and the oceans. But that is going to take a very, very long time, and we can't possibly do that quick enough to avoid the very near-term risk of calamity from climate change. Nature is moving much faster, unfortunately, than we as humans have been able to address in terms of the fundamental solutions, the other two. So next slide, please. So the next question is when? Next slide, please. And here, I think, is the point I've been trying to make. Oh, the conference title doesn't show up there, but global heating emergency, preventing 2 degrees C by 2040. What's the plan? So recent paper, it's a preprint still, but has estimated that there's been a doubling of the decadal rate of global warming in the last decade compared to prior decades. If that rate continues, we are likely to hit 2 degrees C by, you know, the late 2030s or the early 2040s, which should focus the minds. I mean, we are hitting 2 degrees C very soon. So I think the issue now is we need to do something to deploy cooling as soon as possible, because that will reduce the overshoot time. And avoid a lot of the potential large-scale and pretty clear large-scale climate and ecosystem harm. Boselius et al. I have references here, links to papers that back up what I'm saying. Next slide, please. So where? So let's go to the next slide. So we have investigated all the near-term cooling possibilities that we can think of. This is a group within the Healthy Planet Action Coalition, the Urgent Climate Response Group. We have settled on a matrix that I hopefully will have time to show you, that you can look in our website. But basically, because of the mixing, I think there's a lot of lack of understanding in the broader community outside of climate scientists. So I'm speaking to the broader community because I know most of you know very well what I'm talking about. But SAI is because of the way it mixes. It has, first of all, very high leverage, so you just need a little bit of reflectivity, about 1%, to rebalance the energy coming into and going out of the Earth system. And it mixes very homogeneously, first of all, across latitudes, and then across longitudes, and then across latitudes. So it is because of those characteristics, it's uniquely uniform and uniquely efficient and uniquely, you know, it turns out quite cost effective relative to every other method. It appears to be by far and away the most effective tool we have to quickly get some near-term cooling so that we can do the other things we need to do. In order to do targeted, and we advocate a gradual targeted program. I mean, this is another misconception. This is not something you can flip a switch and start. So I've noticed a lot of the simulations start with peak shaving in, let's say 2050 or even earlier. Well, to get peak shaving by 2050, you really have to start testing out pilot tests, looking at the engineering, per my earlier comment, of how to optimize this, how to avoid. There are some adverse effects. We know there could be some adverse effects, but most of them, I think we also know, can be worked around, can be managed, or can be effectively, offset in other ways through careful and balanced SAI deployment. So you would want to start small with gradual deployment, and there have been a lot of papers and studies of this stuff that, in the poles, and the poles is really the only way you can do that because of the stratospheric aerosol injection falls out in the poles. And so, if you want to send it up in the spring and have it fall down in the fall, because that, in the North Pole, and then do the same thing in the South Pole, and you would do it during the sunny times of both poles, then that would be something. If you started very small scale, you might be able to get a signal and measure and evaluate, because you do it and then it falls down pretty quickly and it stays more or less in that area, although it will cool in both poles and hopefully have a beneficial effect on the climate system as a whole, in terms of getting us back to a more sustainable system. These methods could be supplemented by methane emissions reduction and possibly drawdown. So again, short-term, the emissions cuts of short-term, in some places they're calling, short-term, short-lived climate pollutants, basically short-lived species that fall out within, let's say, 10 or 15 years. But the rate of warming is correlated with the emissions rate. So not with the stock, but with the rate of emissions, because they fall out so quickly. So this is a way to sort of do greenhouse gas drawdown by cutting emissions, the easy way. So working on we would advocate prioritizing those things that provide a near-term cooling. The problem with carbon dioxide reduction, I mean, it's not a problem. We have to do it, and we have to do it as soon as possible. But you're basically just slowing down the rate at which things get worse, because it's a stock issue. It just accumulates and takes a long, long time to draw down, unless you don't find a way to draw down more quickly. The other options would be to reverse the relax IMO regulations that have been just imposed on the high seas, the bunker fuel regulations. We have studies. We have actually
Ron,
two papers.
sorry, you have 1 minute left.
Okay, 2 papers in Oxford Open Climate Change that talk about both of these things. And that would be another way to get to reverse the termination shock that we've already had from well-intended regulations to reduce sulfur emissions in bunker fuels. Let me just, if I could go next to slide, it would be slide 12, just in my last minute, the deep dive slide. So yeah, here is our website here, and if you go down one more, please. One more slide, please. Yeah, this is the matrix I'm talking, up, please, to the matrix. Yeah, so up, it keeps flipping back. But anyway, if you go to the website, you will find that matrix of near-term cooling possibilities, and each one of those has a link. So you can go to references that back up some of the things in the table. And in our view, it is really essential that we get to work, we do something that would allow us to cool by 2050. So that, we might have a possibility of avoiding some of these and possibly reversing a little bit some of the tipping points and other calamitous consequences that will happen, we're quite sure, if we don't do SAI plus methane reduction plus some of the other. We have 8 possible. 4 we think will have substantial effect on reducing the risk of near-term cooling points, and 4 that we think might have a modest impact on doing that. So, and we welcome other suggestions, but we think at this point it is really important to think realistically. We are facing a crisis. We need to act soon, and we need to do these things, start testing them, start pilot testing them as soon as possible, and engineering the consequences as well as we can. We just, unfortunately,
Ron, I need to interrupt you.
Out of time.
Over time. Yes.
Thank you, Daniele.
Thank you, Ron. There will be some time for discussion afterwards.
Thank you.
Okay, we get to the last speaker for today. That's Ryan Laughlin. Ryan.
All right. Thanks for the opportunity to talk. I guess I will jump right in. Maybe I should preface this by saying the ethical societal concerns I'm going to talk about are a little bit narrower in scope than the previous talks. So it's just kind of nice. We have a nice range of folks talking about the ethics and governance issues. Next slide, please. So this is a collaborative work. Yeah, Dan and I are working on this together. There's a preprint available. Anyone's welcome to look for it or email me directly if you'd like a copy of the paper. Next slide, please. Okay, so this project is sort of at the intersection of people who believe that some form of solar geoengineering research is warranted, so those who think that we should be doing the research, and this sort of more abstract philosophical question, okay, when is a scientific idea, or in this case, when are certain experiments in times of urgency, in times of controversy, when are those things worth pursuing? Next slide, please. And so our key question is, when is it worth pursuing small-scale field experiments to inform solar geoengineering research? Next slide, please. So the context that we're adopting, this is sort of something that we felt has been missing, is proper acknowledgement of the model-based research context in which a lot of the proposals for field experiments either are talking about or are taking for granted. So, a vast majority of research in solar geoengineering is done using models. Model uncertainties, especially in Earth systems models, shape the design of small-scale field experiments and determine what the potential value of many of these experiments are going to be. If we look at the middle diagram of the short story, is a lot of proposed small-scale field experiments would be intended to improve model representations that are happening inside those smaller grid boxes. And so, of course, climate modeling has been going on for a long time, but this figure on the right here is the different model intercomparison projects as a part of CMIP, and the geoengineering model intercomparison project, GeoMIP, over the years has found both many robust findings. For example, in the idealized experiments, we see different generations of models will overcool the tropics and undercool the poles, and so we've seen some robust findings about what a potential idealized scenario would look like. But also lots of uncertainties have been revealed. Things like what would happen at regional scales in terms of precipitation changes or stratospheric heating or ozone chemistry. And so this has led to more and more questions. And at some point, if we don't sufficiently trust the models, then we need to improve the models. So the framework that we're sort of taking on here is talking about when are experiments worth pursuing such that they would inform how these models are developed continuously and iteratively developed, which in turn can tell us more things about large scale changes of what an SAI scenario would look like. And so that whole thing should be kept in mind. It's just that a lot of times critiques of small scale field experiments sometimes fail to recognize the fundamental role played by climate models in this whole endeavor. And then they offer critiques that are, I would say, oftentimes ethically and politically totally salient, but then also at the same time missing the mark if they're not recognizing what the research actually looks like. Next slide, please. So one way to think about prioritization is to use a risk register. So this risk register comes from McMartin and Kravitz. It's a hypothetical one, right? It's in focus just on sulfate-based SAI. But the idea is if we want to prioritize what to research, we take different aspects of SAI that we're interested in and think about, okay, what aspects of SAI have the highest probability that we're wrong about our knowledge about them, and also would have the worst consequences if we are indeed wrong about them. And then we use that to prioritize. Now, of course, we don't want to fall prey to the illusion of control that a risk register would represent all of the uncertainty out there. All models are wrong. Risk register is like a model to represent our priorities. So all risk registers, strictly speaking, are wrong too, but some can be useful. Next slide, please. So we wanted to start with this idea of the risk register. It's going to tell us some things, but it's also going to lead to questions. So this is not going to be the whole story in terms of pursuit worthiness. So if we think about some examples of hypothetical experiments, looking to the top right, we have experiment number 1, a small scale balloon experiment to measure how a novel non-sulfate based compound would interact with other particles in the stratosphere. So we might say, well, this would help. I mean, there's a large uncertainty, and this could be very harmful if we're wrong in terms of what it does to ozone. So maybe we want to place it up as being a high priority according to the risk register. But then there are other questions, of course, that come up that are not represented here. Some things like, would we have good reason to believe that the information gained from such an experience would be taken up by climate modelers and used to actually improve their models or run new simulations? Or do we have good reasons to believe that the laboratory experiments that have already looked at this are untrustworthy or inadequate? So questions of utility matter. If we look at experiment number 2, that's down in the bottom left, this is an experiment in which marine clouds are seeded from above with sulfate aerosols. And so this could tell us about how cloud forcing would change as a result of SAI. But we could also maybe look and use observational studies following like a volcanic eruption to investigate that. So maybe, provisionally we'll put it in the bottom left. But we can imagine somebody arguing that it should be worth pursuing, a higher priority, maybe thinking just about the risk register. And we would still have additional questions we could ask. Say the experiment is proposed and they're about to go ahead with it. We can ask, well, did the researchers obtain consent from the local community? And did they clearly communicate their research intent when they were seeking that consent? So there was the recent case, I think off the coast of California, I think in Alameda last year, where there was a proposed marine cloud brightening experiment. And then according to the journalists anyway, it was shut down because the researchers didn't seek adequate approval from the local city government. So transparency of intent is important. As a third experiment in the top left, again, a reminder, these are hypothetical, but this is a field experiment where scientists would release 1,000 kilograms of SO2 in the polar stratosphere during March using 3 different technical setups. And we can imagine a case where maybe based on engineering research leading up to this, it was determined that the temperature of the released mixture or the effect of turbulence on the wake of the aircraft, how it would affect plume spreading. These things are uncertainties that would have really bad consequences if we were wrong. So maybe we place them up and to the left. We think we're right, but if we were wrong, it would be really bad. Maybe that's enough to tell us it's pursuit worthy based on the risk register alone. But again, we would have questions we would want to answer. Is the experiment safe? We might say, yeah, because it's the amount of SO2 is orders of magnitude smaller than a volcanic eruption. But then again, the questions of consent from the relevant local community would be something we would want to know about. Next slide, please. So our 4 guiding criteria, these are basically derived from the risk register idea itself, plus some of the questions that arise when trying to think about what the risk register doesn't do for us. So what makes a scientific experiment pursuit worthy? Well, it needs to meet these 4 criteria: scientific rigor, being well designed and evaluated by peer review. So that make sunsets cooling credits thing, by the way, would not even pass this first criterion. It needs to be sufficiently safe. This can be determined based on environmental assessments. It should be deemed useful. And there are 2 parts to this. One is like the risk register idea of utility. And the other one is...
Sorry, you have 1 minute left.
Okay, great. The other is whether there's a good chance that the results would be taken up and actually put to use. That might be hard to determine. And then the last criteria is transparency. So are the experiments designed and its outcomes fully transparent? Did its planning involve sufficient engagement with the relevant communities? Next slide, please. Okay, so we've proposed these as heuristics or guidelines. They're not silver bullet solutions to determining when experiments should be gone ahead with. They're part of a dynamic evaluative process. They should evolve as the research community evolves. And I have one more point to say about that, the research community on the next slide, please. So there's this worry that time sensitivity will increase, and then we might be tempted to relax some of the standards, such as scientific rigor and transparency and safety. And so what I just want to say here is that if the scientific community might be tempted or even coerced into relaxing their standards in the case of a crisis, it's all the more imperative that we ensure fair representation in the scientific and relevant decision-making communities. Next slide, please. And so I just want to end with a reminder of who the solar geoengineering research, who's ultimately this research is meant to serve, which, as the UN One Atmosphere report puts it, is everyone on Earth. So that's the relevant community that's being served by the science. And so that community should be well represented by the scientists too. All right, thank you.
Okay, thank you. Okay, and this concludes our speakers for today. I want to thank everybody for staying on time and for really engaging intellectual conversation and for sharing the results with us. We have some time for session discussion and open to staying a little bit longer if somebody would like to continue the discussion, but we will close the recording at 9:30. So if anybody has any specific questions, and I see a few on the chat. Ryan, do you want to read them yourself and respond, live? You're muted.
Sorry, yes, yeah, I'll respond live. So to Jerry's question, so is there some idea of attributing the effects of small-scale deployments, or are they below detectable levels that can be ignored? The ones that we were thinking of, and Dan, you can correct me if I'm wrong, but they would be below the level of detectability because they're not perturbation experiments. They're really small scale, at least the ones that we were talking about.
I can just add, it depends detecting what, as always, and the point was made in some of the talks, detecting the effects. So on surface climate would require something that is essentially a full-scale deployment. One could consider, however, the detectability of the local changes in atmospheric chemistry and how do you measure that even. So I think we're going to have a few talks on that, plus there's a lot of research that is coming out on that. So detectability of what is sort of the important key. But in general, for a small scale test, one could consider the same thresholds of safety that are used for any other kind of environmental manipulations to understand what can or can't be ignored, or at least. Okay, there's a second question for you.
Oh, let's see. Yes, this is a clarification. So just to clarify, the Alameda experiment that I mentioned did not target marine clouds directly, nor was there a plan to inject SO2. The purpose of the experiment was to study the microphysics and mixing of a saltwater plume from a single sprayer. Okay, that's actually really, that's useful to know because my reading of it, my knowledge of it actually came from a lot of the popular media. And so there definitely was a pretty big disconnect between what the experiment intended to do and how it was reported.
There's a new question from Timmy Tope.
Yeah, it doesn't scroll down automatically. Okay, thanks. What are efforts to get the right stakeholders involved in this discussion? Well, I was running short on time, but the third to last slide, I believe, I mentioned some efforts that I thought were already good, which like the degrees funding initiative to give Global South researchers funding to do their own model-based studies based on their own research questions. And I believe and I'm sure others here are more knowledgeable about this, but I believe there was an AGU SAI ethics initiative specifically aimed at broadening participation in decision makers for SAI. So I would say more of that. Others are welcome to jump in here if they have other ideas.
Okay, and if anybody has any kind of intervention, they can raise their hand, jump in. So Simone, that you had a comment, but sorry, I interrupt somebody. Oh,
No,
Jenny, sorry.
I was just going to follow up on that question about getting the right stakeholders involved in the discussion. In my experience, I've heard from people who felt, coerced or tokenized, right, to get involved. And then if they get involved and are critical or asking certain questions, they're not included. So I think there's, I think it's a delicate, or it's a challenging thing here, with such power imbalances in our world, to say that if every community should have a voice, but we don't have a way to do that, right? And so I just wanted to put that in the discussion.
Great, thank you, Jenny. I see two hands raised, so we have James first and then Ron.
Well, good. I wanted to ask Ron about his whom slide, which might address this issue of who gets to decide, the Lawrence Livermore or the Indonesians. I mean, who gets to geoengineer?
Thank you, James. Yeah, I didn't get to that one, but there's a coordination and governance slide at the end there where I'll just read it out here. The coalition of will. There's three possibilities that we envision. One is a coalition of willing nations and indigenous Arctic peoples, like the sort of on the International Space Station model, devoted to saving the polar ecosystems, sort of like saving the Great Barrier Reef initiative in Australia, where they've been trying to do MCB with little political opposition. Another possibility is a collaborative international effort under the auspices of relevant UN bodies. And the third possibility is self-interested actions by a geopolitical power such as the US, EU, UK, China, Russia, Brazil, India, combination of these and allies. Unfortunately, it turns out that only a small number of companies have the ability to build the kind of planes that would be able to efficiently deliver stratosphere in the mid-latitudes. The US has some that could do polar SAI, but probably not very efficiently. It's hard to say how this will happen, but yes, absolutely, we need to, if we're going to do it in the poles, we would want to discuss and in fact, Operacio Artis is doing that with the Sami Council and other people for the Arctic region through the Arctic Council, and get the permission from them and from the countries that have jurisdiction in those near polar regions, and the South Pole similarly. Although now there we just have Eskimos, so yeah. But one of the things that we as a group in our Oxford Open Climate Change paper emphasize is governance is probably more likely to evolve along with as we try to get more near-term cooling as soon as possible. Like through the IMO, we have a potential for governance, but in other areas right now we don't. But to not do anything until we have ideal governance, I think would be basically just condemning us to a dystopian future, certainly in the near term, possibly for much longer, if we don't try to do something quickly to cool. Sorry, it became a long answer, but I did want to promote that conference that's coming up October. It's at the bottom of one of my early slides, the Preventing the Global Heating Emergency, 2%, 2 degrees Celsius by 2040. What's the plan? We have some very leading international figures, like the lead person on climate change in the UN. We have Pasteur and Pascal and other very prominent climate scientists talking at that conference. And I would really urge, it's an open, it's a an internet conference, so anybody can register, and I think it should be really, really important, and particularly at this time. And full disclosure, I'm one of the speakers as well. But
okay, thank you, Ron and James. I see Simone has her hand up, and I think maybe it can be a wrapping up comment. Maybe if you want, Simone, or not.
It's just the last. There was a question I had in the chat that was for Jenny, but also all in general. When I see also what Ryan said, misinformation in the media, misinformation in general, like what you said, Jenny, is that it sounded like here the scientists, the physical scientists, did not explain well enough that the climate change usually has much larger impact when you in comparison to when you add SAI to it. And there's a general consensus that most effects are smaller or, in a general range. But you kind of stated it more the opposite, that it's worse, that it's getting more and worse than climate change. Is that correct? Is there something that we can do to better exchange information, or where does this come from? Do you understand what I'm saying?
Jenny, if you want to
Are you asking me?
Yes.
Yeah, so the risks of climate change are already devastating to millions of people, right? And they're getting worse and worse. And we're not taking the actions that are needed to reduce those risks, right?
We all agree with that. Yes.
We all agree. So why aren't we focusing on taking those actions to reduce those risks?
Well, we all agree on that. We need to do that. We all agree on that. We need to do actions to do it. And we have the solutions. We know how we do it. We know where to go. There's enough research, a lot of research.
Well, it's not happening because of governance. So like the fact that
But that doesn't answer my question. My question is, SAI usually on the physical side, if you do it in a certain way, can reduce those very bad impacts. But do you agree with that? Or is that somehow that you don't get that out of the literature? That's my question.
I'm saying it can't be done in an equitable, just way that's the same for everyone, right? It's going to make some much worse off, and maybe it will help some, but it could make others even worse.
Well, where does that statement come from? That it makes some way worse off?
The heterogeneity of the science and of the extremes, or could be, we don't, it's unpredictable how it will impact every region.
But is it worse or is it better? That's the big question, right? And that's what we need to answer in this risk assessment, what Ryan said. And I don't want to continue this discussion beyond the time. I'm just saying that could be the discussions we can continue on Wednesday and Thursday.
Okay.
That's all I had. Sorry.
No, thank you. I think this was good, and it's a good thing to discuss. I will close the session, but I saw a hand raised by somebody who hasn't spoken before, and so I would like Dr. K, I think, to speak up since their hand did. I know we need to close, but I'm willing to sacrifice a few more minutes. I saw your hand up. Sorry, Ron, I will not give you the podium again. Yes, please unmute yourself and just speak.
Thanks. It's Chrissy. Thanks.
Oh,
Ben.
hi. Hi, Chrissy. Sorry.
Yeah. So I was gonna say that to buttress what Simone was saying, are we actually ready to bear the risk of climate change as opposed to acting using geoengineering to mitigate some of the impacts that we are going to experience as a result of climate change? I think that is the biggest question that may need to be answered in the future. That if you look at the risk of climate change as compared to maybe, let's say, doing SAI, what are the risks? Are they much more mitigatable if we just continue on the trajectory of climate change? Yeah, thank you.
Okay, we need to close. Actually, I was typing a response to Jenny. So Jenny, I'm not ignoring you. Happy to chat. If you send me an email, I'm happy to talk. I saw that you send me a message, but I really need to close, and people are super late for some people. I want to thank again everybody for joining and for the discussion, and I'll see you tomorrow, most of you tomorrow, I hope, for day 2. Thank you.
Thank you. Thank you all.